In the dark gulf 120 light-years away, a planet circles a dim red sun, a world called K218b. Once just a name in a catalogue, now the stage of something extraordinary. Scientists aimed their instruments at this distant giant and found the strongest hint yet of alien life. Molecules like dimethyl sulfide, a gas on Earth that only living things produce. This isn't science fiction. It's a real-world mystery, shaking everything we thought we knew about life's place in the universe. A planet twice Earth's size, cloaked in thick atmosphere, where water clouds swirl and chemistry teases at the impossible. The universe just got a little louder, and it's asking, are we alone? K218b is an intriguing exoplanet that has captured the attention of astronomers and planetary scientists. Located approximately 124 light-years away from Earth in the constellation Leo, this distant world orbits a red dwarf star known as K218. What makes K218b particularly fascinating is its potential to harbor conditions suitable for life as we know it. Discovered in 2015 using the Kepler Space Telescope, K218b is classified as a super-Earth, meaning it is larger than our home planet, but smaller than the ice giants in our solar system. With a mass roughly 8.5 times that of Earth and a radius about 2.5 times larger, this exoplanet exists in a size range that is not represented in our solar system. Perhaps the most exciting aspect of K218b is its location within its star's habitable zone, the region where temperatures could allow for the existence of liquid water on a planet's surface. This placement, combined with the detection of water vapor in its atmosphere, has led scientists to consider K218b as one of the most promising candidates for potentially habitable worlds beyond our solar system. Recent studies have suggested that K218b might have a substantial hydrogen-rich atmosphere with a water layer underneath, possibly even a water ocean. While this doesn't guarantee the presence of life, it certainly makes K218b a prime target for future observations and studies as we continue our search for potentially habitable worlds in the cosmos. K218b was first discovered in 2015 by astronomers using data from the Kepler Space Telescope during its extended K2 mission. This exoplanet quickly caught the attention of scientists due to its potential habitability. Located approximately 124 light-years away from Earth in the constellation Leo, K218b orbits a red dwarf star known as K218. The discovery of K218b was particularly exciting because it resides within its star's habitable zone, the region where conditions might be right for liquid water to exist on a planet's surface. This factor, combined with its size and mass, which place it in the category of a super-Earth, made it a prime target for further study. Subsequent observations using various instruments, including the Hubble Space Telescope, have revealed more about this intriguing world. In 2019, researchers announced the detection of water vapor in K218b's atmosphere, further fueling interest in this distant planet and its potential to support life as we know it. The story of K218b showcases the rapid advancements in exoplanet detection and characterization. From its initial discovery to the detailed analysis of its atmosphere, this super-Earth continues to provide valuable insights into the diversity of planets beyond our solar system and the possibilities for life elsewhere in the universe. K218b, an intriguing exoplanet that has captured the attention of astronomers, is located approximately 124 light-years away from Earth. This vast distance means that the light we observe from its star today began its journey across space over a century ago. To put this into perspective, if we could travel at the speed of light, which is the fastest speed possible according to our current understanding of physics, it would take us 124 years to reach this distant world. The planet orbits a red dwarf star known as K218, which is smaller and cooler than our Sun. Despite its enormous distance from Earth, modern telescopes and detection methods have allowed scientists to gather remarkable information about K218b. The planet's location in what is considered the habitable zone of its star has made it a subject of great interest in the search for potentially life-supporting worlds beyond our solar system. This considerable distance presents both challenges and opportunities for astronomers. While it makes direct observation difficult, it also provides a diverse range of exoplanets to study, expanding our understanding of planetary formation and the potential for life in the universe. The discovery and study of K218b, despite its vast separation from Earth, demonstrate the incredible advancements in our ability to explore and understand the cosmos. K218b is classified as a super-Earth exoplanet. This means it is a planet outside our solar system with a mass greater than Earth, but significantly less than the ice giants Uranus and Neptune. Super-Earths typically range from about 1.5 to 10 times the mass of Earth. K218b orbits a red dwarf star known as K218, located approximately 124 light-years away from Earth in the constellation Leo. What makes this planet particularly intriguing to astronomers is its position within its star's habitable zone, the region where conditions might allow for the existence of liquid water on the planet's surface. Recent observations have revealed that K218b likely has a substantial atmosphere. Analysis of this atmosphere has detected the presence of water vapor, making it one of the most promising candidates for potential habitability outside our solar system. However, it's important to note that the planet's larger size compared to Earth means it likely has a much higher surface gravity, which could significantly affect its potential to host life as we know it. The discovery and study of planets like K218b are crucial in our quest to understand the diversity of worlds in our galaxy and the potential for life beyond Earth. As our technology and methods for detecting and analyzing exoplanets continue to improve, we may uncover more super-Earths with similar promising characteristics. K218b is significantly larger than Earth, falling into a category of planets known as super-Earths. This exoplanet, discovered in 2015, has a radius approximately 2.5 times that of our home world. To put this into perspective, if we were to place K218b next to Earth, it would appear noticeably bigger, dwarfing our familiar blue marble. The increased size of K218b has important implications for its physical characteristics. Its greater mass results in a stronger gravitational pull, which affects everything from its ability to retain an atmosphere to the potential for plate tectonics. This enhanced gravity would make it challenging for any hypothetical inhabitants to move around, as they would feel much heavier than on Earth. Despite its larger size, K218b is still considered potentially habitable. It orbits within the habitable zone of its star, a region where temperatures could allow for the existence of liquid water on the planet's surface. This combination of size and location makes K218b an intriguing subject for scientists studying the potential for life beyond our solar system. The discovery of planets like K218b highlights the diversity of worlds that exist in our galaxy. As we continue to explore the cosmos, we find that planets come in a wide range of sizes, challenging our understanding of planetary formation and evolution. K218b represents a significant milestone in our quest to find potentially habitable worlds beyond our solar system. This exoplanet, located about 124 light-years away from Earth, orbits a red dwarf star in the constellation Leo. What makes K218b particularly intriguing is its position within the habitable zone of its star, often referred to as the Goldilocks zone, where conditions might be just right for liquid water to exist on its surface. The excitement surrounding K218b stems from the detection of water vapor in its atmosphere, a discovery made using data from the Hubble Space Telescope. This marks the first time we have found water vapor in the atmosphere of an exoplanet within the habitable zone. The presence of water, combined with its estimated temperature range, raises the tantalizing possibility that K218b could support some form of life. However, it is important to note that K218b is much larger than Earth, classified as a super-Earth or mini-Neptune. Its size and mass suggest it might have a thick, hydrogen-rich atmosphere, which could create extreme pressure conditions at the surface. These conditions might be challenging for life as we know it, but they do not necessarily rule out the possibility of life entirely. The study of K218b has pushed forward our understanding of exoplanet atmospheres and the potential for habitability beyond our solar system. It has also demonstrated the capabilities of our current observational techniques and set the stage for future missions, such as the James Webb Space Telescope, which will allow us to probe exoplanet atmospheres in even greater detail. As we continue to explore worlds like K218b, we edge closer to answering one of the most profound questions in science. Are we alone in the universe? K218b received its name through a systematic naming convention used for exoplanets discovered by the Kepler Space Telescope during its extended mission known as K2. The K2 in the name refers to this second phase of the Kepler mission. The number 18 indicates that it was the 18th star system observed during the K2 mission. The lowercase letter b designates that it was the first planet discovered orbiting this particular star. This naming system helps astronomers efficiently catalogue and reference the numerous exoplanets being discovered. It's worth noting that the host star of K218b is simply called K218, following the same logic but without the lowercase letter. K218b has gained significant attention in recent years due to its potential habitability. Located about 124 light-years away from Earth in the constellation Leo, this exoplanet orbits within the habitable zone of its red dwarf star. Its discovery and subsequent studies have provided valuable insights into the diversity of planets beyond our solar system and the potential for finding worlds that could support life as we know it. K218b stands out among known exoplanets due to its potential for habitability and its intriguing atmospheric composition. This distant world, located about 124 light-years from Earth, orbits within the habitable zone of its parent star, a cool red dwarf. This means the planet receives just the right amount of stellar energy to potentially maintain liquid water on its surface, a key ingredient for life as we know it. What truly sets K218b apart is the recent detection of water vapor in its atmosphere. This discovery marks the first time scientists have found water in the atmosphere of an exoplanet orbiting in the habitable zone. Additionally, the planet's atmosphere appears to contain significant amounts of hydrogen and helium, suggesting it might be a mini Neptune rather than a rocky world like Earth. The unique combination of its size, location, and atmospheric composition makes K218b a prime target for future studies. It represents a class of planets not found in our solar system, often referred to as super-Earths or sub-Neptunes. These worlds, larger than Earth but smaller than Neptune, are among the most common planets discovered so far in our galaxy. K218b challenges our understanding of planetary formation and evolution, prompting scientists to reconsider what conditions might be necessary for life to exist beyond Earth. Its discovery and ongoing study are pushing the boundaries of exoplanet research and bringing us closer to answering the age-old question: are we alone in the universe? K218b was initially discovered using the Kepler Space Telescope during its extended K2 mission. This powerful space observatory was designed to search for exoplanets by detecting the tiny dips in starlight that occur when a planet passes in front of its host star. The Kepler telescope used a method called transit photometry, which involves precisely measuring the brightness of stars over time to detect these periodic dimming events. After its initial discovery, K218b was further studied using the Hubble Space Telescope. Hubble's Wide Field Camera 3 was employed to analyze the planet's atmosphere through a technique called transmission spectroscopy. This method involves studying the starlight that passes through the planet's atmosphere during a transit, allowing scientists to identify the presence of various molecules. Ground-based observatories also played a role in studying K218b. The High-Accuracy Radial Velocity Planet Searcher, or HARPS, spectrograph at the European Southern Observatory's La Silla facility in Chile was used to measure the planet's mass. This instrument detects the tiny wobbles in a star's motion caused by the gravitational pull of orbiting planets. The combined data from these instruments provided scientists with crucial information about K218b's size, mass, orbit, and atmospheric composition, making it one of the most well-studied potentially habitable exoplanets to date. Our knowledge of K218b has expanded significantly since its initial detection in 2015. This exoplanet, located about 124 light-years from Earth, has become a focal point for astronomers studying potentially habitable worlds beyond our solar system. Initially, K218b was identified as a super-Earth, a planet larger than our own but smaller than ice giants like Neptune. Further observations revealed its mass to be about 8 times that of Earth, placing it in a category scientists call sub-Neptunes. This classification sparked debates about whether K218b could support life as we know it. A major breakthrough came in 2019 when researchers using the Hubble Space Telescope detected water vapor. A major breakthrough came in 2019 when researchers using the Hubble Space Telescope detected water vapor in K218b's atmosphere. This discovery marked the first time water had been found in the atmosphere of an exoplanet within the habitable zone of its star. The habitable zone is the region around a star where temperatures could allow liquid water to exist on a planet's surface. More recent studies have refined our understanding of K218b's composition and potential habitability. Scientists now believe the planet likely has a large hydrogen and helium atmosphere surrounding a layer of high-pressure water. Deeper still, there might be an Earth-like rocky core. While these conditions differ from Earth, they do not rule out the possibility of life, prompting researchers to consider new models of potentially habitable worlds. K218b orbits a red dwarf star known as K218. Red dwarfs are the most common type of star in our galaxy, making up about 75% of all stars in the Milky Way. These stars are smaller and cooler than our Sun, typically ranging from 1/3 to 1/2 the mass and size of our home star. The relatively cool temperature of red dwarfs means they emit most of their light in the red and infrared parts of the spectrum, giving them their characteristic reddish hue. Despite their small size, red dwarfs have incredibly long lifespans, often lasting for trillions of years due to their slow rate of fuel consumption. This longevity makes planets orbiting red dwarfs particularly interesting in the search for potentially habitable worlds. The stable environment provided by these long-lived stars could allow more time for life to potentially emerge and evolve on any suitable planets in their systems. However, orbiting a red dwarf also presents challenges for potential habitability. These stars are prone to frequent and intense flares, which could strip away planetary atmospheres over time. The close orbits required for planets to be in the habitable zone of these cool stars also raises the possibility of tidal locking, where one side of the planet always faces the star. K218b orbits a red dwarf star known as K218, which differs significantly from our Sun. This star is much smaller and cooler than our solar system's central star. While our Sun is classified as a yellow dwarf, K218 falls into the category of red dwarfs, the most common type of star in our galaxy. The size difference is stark, with K218 being only about half the size of our Sun. This smaller size correlates with a lower mass, as K218 has only about 40% of the Sun's mass. The temperature at the surface of K218 is also considerably cooler, reaching only about 3,200 degrees Celsius, compared to the Sun's scorching 5,500 degrees Celsius. Red dwarf stars like K218 are known for their longevity. While our Sun is expected to have a lifespan of about 10 billion years, K218 could continue shining for trillions of years. This extended lifespan is due to the star's ability to burn hydrogen more slowly and efficiently than larger stars. Despite these differences, K218 still provides enough heat and light to potentially support life on planets orbiting within its habitable zone, making systems like this intriguing targets in the search for potentially habitable worlds beyond our solar system. The K218 system contains at least 2 known planets orbiting the red dwarf star K218. This star system has garnered significant attention from astronomers due to its potential for harboring habitable worlds. The first planet discovered in this system, designated K218b, is a super-Earth that orbits within the star's habitable zone. This region is where conditions might be suitable for liquid water to exist on a planet's surface, making it a prime target for the search for extraterrestrial life. The second confirmed planet in the system is K218c, which orbits closer to the star and is likely too hot to support life as we know it. This planet was discovered through follow-up observations after the initial detection of K218b. Both planets were found using the transit method, where astronomers detect the slight dimming of a star's light as a planet passes in front of it. While only 2 planets have been confirmed in the K218 system so far, it is possible that additional planets may be discovered as our observational techniques and technologies improve. Many red dwarf stars are known to host multiple planets, often in compact orbital configurations. As we continue to study this intriguing system, we may uncover more celestial bodies orbiting K218, potentially expanding our understanding of planetary formation and the potential for life beyond Earth. K218b, an intriguing exoplanet that has captured the attention of astronomers, completes one orbit around its host star in approximately 33 Earth days. This relatively short orbital period places K218b much closer to its star than Earth is to the Sun. However, because K218b orbits a red dwarf star, which is cooler and less luminous than our Sun, the planet still resides within the habitable zone of its system. The rapid orbit of K218b provides scientists with frequent opportunities to study the planet as it transits in front of its star. These regular transits allow researchers to gather data about the planet's atmosphere and composition, making K218b an excellent target for ongoing exoplanet studies. This swift journey around its star also means that a year on K218b passes very quickly by Earth standards. An observer on the planet's surface would experience the equivalent of about 11 Earth years in the span of just one Earth year. This rapid cycle of seasons, if they exist on K218b, would create a dynamic and ever-changing environment, quite different from what we experience on our home planet. The K218 system is significantly younger than our solar system. While our Sun and planets formed roughly 4.5 billion years ago, the K218 system is estimated to be only about 2 billion years old. This means that K218 and its planets have had less time to evolve and develop compared to Earth and our neighboring worlds. Despite its relative youth, the K218 system has already captured the attention of astronomers and exoplanet hunters. The star at the center of this system, K218, is a red dwarf, smaller and cooler than our Sun. These types of stars are known for their longevity, often remaining stable for tens of billions of years. The age difference between K218 and our solar system provides an interesting opportunity for scientists to study planetary formation and evolution at different stages. By comparing the characteristics of planets in the K218 system to those in our own, researchers can gain insights into how planets change over time and how factors like stellar age might influence the potential for life to emerge and thrive. As we continue to explore and study distant star systems like K218, we gain a broader perspective on the diversity of planetary systems in our galaxy and how they develop across cosmic timescales. The habitable zone is the region around a star where conditions might be just right for liquid water to exist on the surface of a planet. This area is often called the Goldilocks zone because it is not too hot and not too cold. The habitable zone's exact location varies depending on the star's size and temperature. For larger, hotter stars, it is farther out, while for smaller, cooler stars, it is closer in. K218b is a particularly intriguing exoplanet that orbits within the habitable zone of its star, a red dwarf known as K218. This planet is located about 124 light-years from Earth in the constellation Leo. K218b is larger than Earth, falling into a category we call super-Earths. Its position within the habitable zone makes it a prime candidate for potential habitability. What makes K218b even more exciting is that astronomers have detected water vapor in its atmosphere. This discovery, combined with its location in the habitable zone, has sparked intense interest in the scientific community. However, it is important to note that being in the habitable zone does not guarantee that a planet is habitable. Many other factors, such as the planet's composition, atmosphere, and magnetic field, play crucial roles in determining whether life as we know it could exist there. The study of K218b and other exoplanets in habitable zones is pushing the boundaries of our understanding of planetary formation and the potential for life beyond our solar system. As we develop more advanced observation techniques and instruments, we may soon be able to learn even more about these distant worlds and their potential to harbor life. K218b orbits its star at a distance that places it within the habitable zone, much like Earth's position relative to our Sun. However, the comparison is not straightforward due to the differences between the two stars. K218b's host star is a red dwarf, which is smaller and cooler than our Sun. As a result, the habitable zone around this star is much closer in than the one surrounding our Sun. The exoplanet K218b actually orbits its star at about 1/7 the distance between Earth and the Sun. Despite this seemingly close proximity, the planet receives a similar amount of energy from its star as Earth does from the Sun. This is because the red dwarf star emits less heat and light than our Sun, allowing K218b to maintain potentially habitable conditions even at this closer orbit. This arrangement showcases the diversity of planetary systems in our galaxy. It demonstrates that habitable conditions can exist in configurations quite different from our own solar system, expanding our understanding of where life might potentially exist beyond Earth. K218b orbits a red dwarf star, which significantly influences its potential habitability. Red dwarfs are smaller and cooler than our Sun, emitting less energy. This means K218b needs to orbit much closer to its star to receive enough warmth for liquid water to potentially exist on its surface. However, this proximity comes with challenges. The star's reduced size and temperature result in a narrow habitable zone, the region where conditions might support life as we know it. K218b's close orbit places it within this zone, but it also exposes the planet to intense stellar activity. Red dwarfs are known for their volatile nature, frequently unleashing powerful flares and radiation bursts. These stellar outbursts could pose serious threats to any potential life on K218b. The intense radiation might strip away the planet's atmosphere over time or make its surface inhospitable. Additionally, the close orbit likely causes K218b to be tidally locked, meaning one side always faces the star. This could create extreme temperature differences between the day and night sides of the planet. Despite these challenges, K218b's larger size compared to Earth might provide some protection. Its stronger gravity could help retain its atmosphere against the stellar onslaught, potentially shielding the surface and maintaining conditions favorable for liquid water. The complex interplay between the star's influence and the planet's characteristics makes K218b a fascinating subject in the search for potentially habitable worlds beyond our solar system. The K218 star system holds several intriguing features beyond its potentially habitable exoplanet. K218 itself is a red dwarf star, smaller and cooler than our Sun, located about 124 light-years from Earth in the constellation Leo. This star is particularly interesting to astronomers due to its relative stability compared to other red dwarfs, which often exhibit intense flare activity that could be detrimental to life. In addition to K218b, the exoplanet that has garnered much attention for its potential habitability, the system is thought to host at least one other planet, K218c. This second planet orbits closer to the star and is likely too hot to support life as we know it. The presence of multiple planets in the system provides valuable data for understanding planetary formation and evolution around red dwarf stars. The K218 system also offers a unique opportunity for atmospheric study. The size and proximity of K218b to its star make it an excellent candidate for transit spectroscopy, allowing scientists to analyze its atmosphere in detail. This has led to the exciting detection of water vapor in its atmosphere, a crucial component for life as we understand it. Furthermore, the system's relatively close distance to Earth makes it a prime target for future observations with advanced telescopes. As our technology improves, we may uncover more secrets about this intriguing star system, potentially shedding light on the prevalence of habitable worlds in our galaxy. The K218 system presents an intriguing case for astronomers studying planetary stability. Unlike our solar system, which has remained relatively stable for billions of years, the K218 system shows some key differences that could affect its long-term equilibrium. K218 is a red dwarf star, smaller and cooler than our Sun. Its planets orbit much closer to their host star compared to Earth's distance from the Sun. This proximity can lead to stronger gravitational interactions between the planets and the star, potentially causing more frequent orbital shifts over time. The system is known to have at least 2 planets, with K218b being of particular interest due to its potential habitability. However, the presence of additional undiscovered planets could further complicate the system's dynamics. These unseen bodies might exert gravitational influences that could alter the orbits of known planets over long periods. While our solar system has had billions of years to settle into its current configuration, The K218 system is still relatively young and may continue to evolve. Astronomers are keen to observe this system over extended periods to better understand its stability and how it compares to our own cosmic neighborhood. K218b is an intriguing exoplanet that has captured the attention of astronomers and planetary scientists. Current estimates suggest that K218b has a mass approximately 8 times that of Earth. This places it in a category known as super-Earths or mini-Neptunes, depending on its composition and structure. The mass of K218b was determined through careful observations and analysis of its gravitational effects on its host star. By measuring tiny wobbles in the star's position, scientists can infer the presence and mass of orbiting planets. This technique, called the radial velocity method, has been crucial in our understanding of exoplanets. It's important to note that while we have a good estimate of K218b's mass, there is still some uncertainty. As our observational techniques improve and we gather more data, we may refine this estimate further. The mass of an exoplanet is a key factor in determining its potential habitability and internal structure. Understanding the mass of K218b helps scientists make educated guesses about its composition. With 8 times the mass of Earth, it could be a rocky world with a thick atmosphere or a planet with a significant portion of its mass as water or ice. This makes K218b an exciting target for future studies as we seek to understand the diversity of planets in our galaxy. K218b is an exoplanet that has captured the attention of astronomers due to its potential habitability. This distant world orbits a red dwarf star known as K218, located about 124 light-years away from Earth in the constellation Leo. The radius of K218b is estimated to be approximately 2.5 times that of Earth. This places it in a category of planets called super-Earths, which are larger than our home world but smaller than the ice giants like Neptune and Uranus in our solar system. The size of K218b is particularly intriguing because it falls within a range where the planet could be either rocky like Earth or have a substantial gaseous envelope. This uncertainty about its composition adds to the excitement surrounding this exoplanet. Its larger size compared to Earth means it would have a stronger gravitational pull, which could affect the planet's atmosphere, surface conditions, and potential for hosting life as we know it. Understanding the radius of exoplanets like K218b is crucial for scientists as they work to classify these distant worlds and assess their potential habitability. The methods used to determine such measurements often involve observing the dimming of the host star as the planet passes in front of it, a technique known as the transit method. This approach allows astronomers to calculate the planet's size relative to its star, providing valuable insights into the nature of these far-off celestial bodies. K218b, an exoplanet that has captured the attention of astronomers, has a surface gravity significantly higher than Earth's. Based on current estimates, the surface gravity on K218b is approximately 2.5 times stronger than what we experience on our home planet. This means that if you were to stand on the surface of K218b, you would feel much heavier than you do on Earth. The increased gravity is due to K218b's larger size and mass compared to Earth. It is classified as a super-Earth, a type of planet that is more massive than our world, but less massive than the ice giants in our solar system, such as Neptune and Uranus. The stronger gravitational pull on K218b would have profound effects on its physical characteristics and potential for life as we know it. This higher gravity would influence many aspects of the planet's environment. It could lead to a denser atmosphere, as the stronger gravitational force would be more effective at holding gases close to the surface. The increased gravity might also affect the planet's geological processes, potentially resulting in a flatter surface with fewer dramatic elevation changes compared to Earth. For any hypothetical life forms on K218b, adapting to this stronger gravity would be crucial. They would likely evolve to have stronger muscles and bones to support their weight, and their bodies would be shaped to distribute mass more efficiently. The study of K218b's gravity provides valuable insights into the diversity of planetary conditions in our galaxy, and helps us understand the potential for life beyond our solar system. K218b, an exoplanet located about 124 light-years from Earth, has captured the attention of astronomers due to its potential habitability. Based on current models and observations, scientists estimate that the temperature range on K218b could be between -20 degrees Celsius and 60 degrees Celsius. This wide range encompasses temperatures we experience on Earth, from freezing conditions to hot summer days. The planet's position in the habitable zone of its star, a cool red dwarf, contributes to these temperature estimates. However, it's important to note that these figures are based on theoretical models and limited observational data. The actual temperatures on K218b could vary depending on factors such as its atmospheric composition, cloud cover, and potential greenhouse effects. Interestingly, recent studies have detected the presence of water vapor in K218b's atmosphere, further fueling speculation about its potential to support life as we know it. The temperature range, combined with the presence of water, makes K218b an intriguing target for future exoplanet research and the search for potentially habitable worlds beyond our solar system. K218b is a fascinating exoplanet that has captured the attention of astronomers and planetary scientists. Current observations and models suggest that K218b is likely a mini-Neptune rather than a rocky Earth-like planet. This means it probably does not have a solid surface as we might imagine, but instead has a thick, gaseous atmosphere surrounding a smaller, denser core. The planet's size and mass indicate that it falls into a category between Earth and Neptune, often referred to as a sub-Neptune or mini-Neptune. These types of planets are believed to have a structure consisting of a rocky or icy core enveloped by a substantial hydrogen and helium atmosphere. This atmosphere is much more extensive than Earth's, making up a significant portion of the planet's volume. While K218b's atmosphere contains water vapor and possibly liquid water clouds, this doesn't mean there's a water ocean on a solid surface. Instead, the water is likely dispersed throughout the thick atmosphere, potentially forming a diffuse layer of supercritical fluid deep within the planet where temperatures and pressures are extremely high. The nature of K218b highlights the diversity of planets we're discovering beyond our solar system. It challenges our understanding of planetary formation and evolution, showing us that the universe contains worlds quite different from the familiar rocky and gas giants in our own cosmic backyard. K218b, an exoplanet discovered in 2015, has captured the attention of astronomers due to its potential habitability. Recent studies suggest that its atmosphere might contain a mix of hydrogen, helium, and water vapor. This combination is particularly exciting because the presence of water vapor indicates the possibility of liquid water on the planet's surface. Observations using the Hubble Space Telescope have revealed strong evidence for water vapor in K218b's atmosphere. Additionally, scientists believe that methane and nitrogen might also be present, though in smaller quantities. The exact ratios of these gases are still uncertain and subject to ongoing research. It's important to note that K218b is significantly larger than Earth, classified as a super-Earth or mini-Neptune. This size difference means its atmosphere is likely much thicker and more extensive than Earth's. The planet's atmospheric composition and structure are crucial factors in determining its potential to support life as we know it. As our observational techniques and instruments improve, we expect to refine our understanding of K218b's atmosphere. Future missions, such as the James Webb Space Telescope, will provide more detailed data, allowing us to better characterize the atmospheric composition of this intriguing exoplanet and others like it. K218b, an exoplanet discovered in recent years, has captured the attention of astronomers due to its potential habitability. When comparing its density to Earth, we find some intriguing differences. K218b is significantly less dense than our home planet. While Earth has a density of about 5.5 grams per cubic centimeter, K218b's density is estimated to be closer to 3 grams per cubic centimeter. This lower density suggests that K218b has a different composition from Earth. It likely has a larger proportion of lighter elements, particularly water. Scientists believe that K218b could be what we call a water world, with a substantial portion of its mass consisting of water in various forms, from ice to liquid to vapor. The difference in density between K218b and Earth also impacts the planet's surface gravity. Despite being larger and more massive than Earth, K218b's lower density means that its surface gravity might be similar to, or even less than Earth's. This has important implications for the potential habitability of the planet and the types of atmospheres it could maintain. Understanding the density of exoplanets like K2-18b is crucial in our quest to find potentially habitable worlds beyond our solar system. It provides valuable insights into the planet's composition, structure, and the conditions that might exist on its surface or within its atmosphere. The exoplanet K2-18b orbits a red dwarf star approximately 124 light-years from Earth in the constellation Leo. Current observations and models suggest that K2-18b is likely tidally locked to its host star, meaning the same side of the planet always faces the star. This phenomenon occurs when a planet's orbital period matches its rotational period, resulting in one hemisphere experiencing perpetual daylight while the other remains in constant darkness. Tidal locking is common for planets orbiting close to their stars, especially around smaller, cooler stars like red dwarfs. The gravitational forces exerted by the star gradually slow the planet's rotation until it synchronizes with its orbit. For K2-18b, which completes an orbit around its star in approximately 33 Earth days, this process has likely already occurred. The tidally locked nature of K2-18b has significant implications for its potential habitability and climate. The stark temperature differences between the day and night sides could drive powerful winds and create unique weather patterns. However, the planet's location in the habitable zone of its star and the detection of water vapor in its atmosphere make it an intriguing target for further study in the search for potentially habitable worlds beyond our solar system. K2-18b, an intriguing exoplanet that has captured the attention of astronomers, is believed to be approximately 2 billion years old. This age estimate places it as a relatively mature planet, having formed long after the birth of its host star, K2-18. The age of K2-18b is determined through various methods, including studying the properties of its parent star and comparing the planet's characteristics to models of planetary evolution. It's important to note that determining the precise age of an exoplanet is a challenging task, and this estimate comes with some uncertainty. Astronomers use a combination of observations and theoretical models to arrive at this figure. The age of K2-18b provides valuable insights into its potential habitability and the evolution of planets in other star systems. At 2 billion years old, K2-18b has had considerable time to develop and stabilize its atmosphere and internal structure. This age also suggests that if life were to exist on this planet, it would have had a significant period to potentially emerge and evolve, assuming conditions on the planet are favorable for such processes. K2-18b is a fascinating exoplanet that has captured the attention of astronomers and astrobiologists alike. This super-Earth, located about 124 light-years away from us, orbits within the habitable zone of its red dwarf star. Its size and mass suggest it could be a rocky world with a substantial atmosphere, potentially creating conditions conducive to life as we know it. The planet's mass, estimated to be about 8 times that of Earth, results in stronger gravity on its surface. This increased gravitational pull could lead to a denser atmosphere, potentially providing better protection against harmful stellar radiation. The atmosphere might also help regulate surface temperatures, creating a more stable environment for potential life forms. K2-18b's orbit places it in the habitable zone, where liquid water could exist on the surface. The presence of water is crucial for life as we understand it, and recent observations have detected water vapor in the planet's atmosphere. This discovery significantly boosts the planet's potential for habitability. However, the planet's host star, a red dwarf, presents challenges. Red dwarfs are known for their volatile nature, often emitting powerful flares that could strip away planetary atmospheres over time. The intense radiation could also be harmful to any life on the surface. Despite these challenges, the potential for life on K2-18b remains an exciting possibility, driving further research and observations of this intriguing world. K2-18b has captured the attention of astronomers due to compelling evidence suggesting the presence of an atmosphere. This exoplanet, located about 124 light-years from Earth, has been the subject of intense study using advanced space telescopes and sophisticated analysis techniques. One of the most significant pieces of evidence comes from observations made by the Hubble Space Telescope. Using a method called transit spectroscopy, scientists detected the signatures of water vapor in the planet's atmosphere. This discovery was groundbreaking, as it marked the first time water vapor was detected in the atmosphere of a potentially habitable planet outside our solar system. Further studies have also indicated the possible presence of hydrogen and helium in K2-18b's atmosphere. These lighter elements are often found in the atmospheres of larger planets, suggesting that K2-18b might have a substantial gaseous layer. The detection of these elements, along with water vapor, strongly supports the existence of an atmosphere. Moreover, the planet's density measurements, derived from its mass and radius, are consistent with a world that has a rocky core surrounded by a significant atmospheric envelope. This combination of spectroscopic data and physical characteristics provides robust evidence for an atmosphere on K2-18b, making it a prime target for future studies in the search for potentially habitable worlds beyond our solar system. Astronomers used a technique called transit spectroscopy to detect and analyze the atmosphere of K2-18b. This method involves observing the planet as it passes in front of its host star. As the planet transits, starlight filters through its atmosphere, and different gases absorb specific wavelengths of light. By carefully studying the resulting spectrum, scientists can identify the chemical components present in the planet's atmosphere. The Hubble Space Telescope played a crucial role in these observations. Its Wide-Field Camera 3 captured the transit data, allowing researchers to detect the signature of water vapor in K2-18b's atmosphere. This discovery was particularly exciting because K2-18b orbits within its star's habitable zone, where liquid water could potentially exist on the planet's surface. Follow-up observations using other telescopes and instruments have helped refine our understanding of K2-18b's atmospheric composition. Ground-based telescopes equipped with high-resolution spectrographs have provided additional data, allowing scientists to search for other molecules and study the planet's atmospheric dynamics. As our technology and observational techniques continue to improve, we expect to gain even more detailed insights into the atmospheres of exoplanets like K2-18b. Future missions, such as the James Webb Space Telescope, will offer unprecedented capabilities for studying these distant worlds and potentially uncovering signs of habitability or even life beyond our solar system. K2-18b, an exoplanet located about 124 light-years from Earth, has captured the attention of astronomers due to its intriguing atmosphere. Recent studies have revealed that this super-Earth, which is about 8 times the mass of our planet, possesses an atmosphere rich in hydrogen, helium, and water vapor. These findings have sparked excitement in the scientific community, as the presence of water vapor suggests the potential for liquid water on the planet's surface. Spectroscopic observations have also detected methane and carbon dioxide in K2-18b's atmosphere. The presence of these molecules is particularly interesting because they are considered potential biosignatures, meaning they could indicate the possibility of life. However, it's important to note that the detection of these gases alone does not confirm the existence of life on the planet. Another fascinating component of K2-18b's atmosphere is the potential presence of ammonia. This compound could play a crucial role in the planet's atmospheric chemistry and might contribute to its habitability. The combination of these atmospheric components creates a unique environment that differs significantly from what we observe on Earth or other planets in our solar system. The study of K2-18b's atmosphere continues to evolve as scientists employ more advanced techniques and instruments. Future observations with next-generation telescopes may reveal additional components and provide a more detailed understanding of this distant world's atmospheric composition and potential habitability. K2-18b, an exoplanet discovered in 2015, orbits a red dwarf star about 111 light-years from Earth. This intriguing world has captured the attention of astronomers due to its potential habitability. When it comes to atmospheric pressure, K2-18b presents a stark contrast to our home planet. The atmospheric pressure on K2-18b is estimated to be significantly higher than Earth's. While Earth's sea level pressure is about 1 bar, scientists believe K218b could have a pressure ranging from tens to hundreds of bars. This extreme pressure is a result of the planet's greater mass and size compared to Earth, as well as its thick atmosphere composed primarily of hydrogen and helium. Such high atmospheric pressure would create an environment vastly different from what we experience on Earth. It would compress gases, alter chemical reactions, and potentially give rise to exotic states of matter. The intense pressure could also affect the behavior of any potential liquids on the planet's surface, changing their boiling points and other properties. Understanding the atmospheric pressure on K218b is crucial for assessing its potential habitability and the types of life forms that could theoretically exist there. While the high pressure poses challenges for life as we know it, it also opens up possibilities for unique adaptations and chemical processes that might support novel forms of life. K218b's atmosphere plays a crucial role in its potential habitability. This exoplanet, located about 124 light-years from Earth, has captured the attention of scientists due to its size and position within its star's habitable zone. The atmosphere of K218b is particularly intriguing because it contains significant amounts of water vapor, a key ingredient for life as we know it. The presence of water in K218b's atmosphere suggests the possibility of a water cycle similar to Earth's, which could create conditions conducive to life. Moreover, the atmosphere acts as a protective shield, potentially shielding the planet's surface from harmful radiation emitted by its host star. This protective function is essential for the development and sustainability of life forms. Another important aspect of K218b's atmosphere is its ability to regulate temperature. The greenhouse effect caused by certain gases in the atmosphere could help maintain temperatures within a range suitable for liquid water to exist on the surface. This temperature regulation is critical for creating stable conditions that could support life. However, it's important to note that while the atmosphere of K218b shows promising signs, there are still many unknowns. The planet's larger size compared to Earth means it likely has a much denser atmosphere, which could create very different conditions from those we're familiar with. Scientists continue to study this intriguing world, hoping to unravel more secrets about its atmospheric composition and its potential to harbor life. K218b, an exoplanet about twice the size of Earth, has captured the attention of astronomers due to its intriguing atmosphere. One of the most exciting features is the potential presence of water vapor. This discovery marks the first time water vapor has been detected in the atmosphere of a planet in the habitable zone of its star, where liquid water could exist on the surface. The atmosphere of K218b also contains significant amounts of hydrogen and helium, which is not surprising given its size. However, what makes it truly unique is the possibility of exotic forms of water existing in its atmosphere. Under the intense pressure and temperature conditions on K218b, water might exist in a supercritical state, blurring the line between liquid and gas. Another fascinating aspect of K218b's atmosphere is the potential presence of methane and ammonia. These compounds, if confirmed, could indicate complex chemical processes occurring on the planet. The combination of water vapor, methane, and ammonia is particularly intriguing as it resembles the composition of atmospheres where life might potentially develop. The study of K218b's atmosphere is ongoing, and scientists are eager to use more advanced instruments to probe its composition further. The James Webb Space Telescope, with its unprecedented sensitivity, is expected to provide even more detailed information about this extraordinary exoplanet's atmospheric features in the near future. The atmosphere of K218b, an exoplanet that has garnered significant attention in recent years, presents an intriguing case for atmospheric stability. This super-Earth, located about 124 light-years from our solar system, orbits within the habitable zone of its cool dwarf star. Current observations and models suggest that K218b's atmosphere is likely to be relatively stable over long periods. This stability is partly due to the planet's size and mass, which are sufficient to retain a substantial atmosphere against the pressures of stellar radiation and potential atmospheric escape mechanisms. The presence of water vapor and possibly clouds in K218b's atmosphere, as detected by the Hubble Space Telescope, further supports the idea of a stable atmospheric composition. water vapor can act as a regulating factor, helping to maintain temperature balance and chemical equilibrium within the atmosphere. However, it's important to note that our understanding of K2-18b's atmospheric stability is based on limited data and theoretical models. Future observations with more advanced telescopes will provide a clearer picture of the long-term dynamics and evolution of this intriguing exoplanet's atmosphere. The discovery of water vapor in the atmosphere of K2-18b marks a significant milestone in our search for potentially habitable worlds beyond our solar system. This exoplanet, located about 110 light-years from Earth, orbits within the habitable zone of its star, where temperatures could allow liquid water to exist on its surface. The presence of water vapor suggests that K2-18b might have a water cycle similar to Earth's, with the potential for clouds, rain, and even oceans. This finding is particularly exciting because water is a crucial ingredient for life as we know it. While K2-18b is much larger than Earth, classified as a super-Earth or mini-Neptune, the detection of water in its atmosphere opens up new possibilities for understanding the diversity of potentially habitable worlds in our galaxy. However, we must be cautious in our interpretations. The presence of water vapor alone does not guarantee habitability. Other factors, such as the planet's size, gravity, and overall atmospheric composition, play crucial roles in determining whether it could support life. Scientists are eager to conduct further observations to better understand the conditions on K2-18b and similar exoplanets. This discovery also demonstrates the power of our current and future observational technologies. As we continue to refine our methods and launch more advanced telescopes, we may soon be able to detect biosignatures, chemical markers of life, in the atmospheres of distant worlds, bringing us closer to answering the age-old question, are we alone in the universe? K2-18b, an exoplanet orbiting a red dwarf star, experiences a complex interaction between its atmosphere and the radiation from its host star. The planet's atmosphere, composed primarily of hydrogen and helium with traces of water vapor, acts as a protective shield against the intense stellar radiation. The star's ultraviolet and X-ray emissions interact with the upper layers of K2-18b's atmosphere, causing ionization and chemical reactions. This process can lead to the formation of new compounds and potentially create a layer similar to Earth's ozone, which helps protect the planet's surface from harmful radiation. As the star's energy penetrates deeper into the atmosphere, it encounters water vapor molecules. These molecules absorb certain wavelengths of light, particularly in the infrared spectrum, contributing to the planet's greenhouse effect and helping to maintain its temperature. The atmospheric circulation patterns on K2-18b are likely influenced by the uneven heating from its star. This could result in strong winds and potentially create distinctive cloud formations or storm systems, further shaping the planet's climate and its ability to interact with stellar radiation. The atmosphere of K2-18b offers a fascinating glimpse into the planet's past and its potential future. This super-Earth, located about 124 light-years away, has captured the attention of astronomers due to its intriguing atmospheric composition. Recent observations have revealed the presence of water vapor in K2-18b's atmosphere, a discovery that provides valuable clues about the planet's formation and evolution. The detection of water suggests that K2-18b may have formed farther out in its solar system, beyond the snow line where water can exist as ice, and then migrated inward to its current orbit. This migration theory aligns with our understanding of how some exoplanets evolve over time. Moreover, the atmosphere of K2-18b contains significant amounts of hydrogen and helium, indicating that the planet has managed to retain much of its primordial atmosphere. This retention tells us that K2-18b has likely not experienced the same level of atmospheric loss as some other exoplanets, possibly due to its size and the characteristics of its host star. The presence of these light elements also suggests that the planet may have a substantial gaseous envelope surrounding a rocky or icy core. The atmospheric composition of K2-18b also hints at the possibility of ongoing geological processes. The potential presence of methane and ammonia, though not yet confirmed, could indicate active volcanism or other internal processes that continue to shape the planet's atmosphere. As we continue to study K2-18b, Its atmosphere will undoubtedly reveal more about its dynamic history and its potential to support various forms of chemistry, possibly even laying the groundwork for conditions conducive to life as we know it. Recent observations of the exoplanet K218b have revealed compelling evidence for the presence of water in its atmosphere. This distant world, located about 124 light-years from Earth, has captured the attention of astronomers and planetary scientists alike. Using data from the Hubble Space Telescope, researchers detected the signature of water vapor in the planet's atmosphere. This discovery was made possible through a technique called transit spectroscopy. The James Webb Space Telescope, with its advanced capabilities, is expected to provide even more detailed information about K218b's atmosphere in the future, potentially revealing more about its composition and habitability. Water on K218b likely exists in multiple forms due to the planet's unique characteristics. This distant world, located about 124 light-years from Earth, is classified as a super-Earth or mini-Neptune. Its size and mass suggest it has a rocky core surrounded by a thick atmosphere. Given the temperature and pressure conditions on K218b, water could exist as a gas in the upper atmosphere, forming clouds similar to those on Earth. As we descend through the atmosphere, increasing pressure and temperature might allow for liquid water to form, creating a layer where water droplets could float or fall as rain. Deeper still, where pressures become extreme, water might enter an exotic state known as a supercritical fluid. In this form, water behaves like both a liquid and a gas simultaneously, possessing properties of each. This supercritical water could form a vast, deep layer around the planet's core. At the boundary between the rocky core and the water layer, if temperatures are low enough, water might even exist as ice, but in forms unlike what we see on Earth. These could include high-pressure ice phases with crystal structures different from ordinary ice, showcasing the diverse forms water can take in the extreme conditions of distant worlds. Scientists discovered water on K218b using a sophisticated technique called transit spectroscopy. This method involves analyzing the light from the planet's host star as it passes through the planet's atmosphere during a transit. When K218b moves in front of its star, some of the starlight filters through the planet's atmosphere before reaching Earth. Different molecules in the atmosphere absorb specific wavelengths of light, creating a unique spectral signature. By carefully examining this signature, researchers can identify the presence of various compounds, including water vapor. In the case of K218b, astronomers used data from the Hubble Space Telescope to detect the telltale signs of water molecules in the planet's atmosphere. This groundbreaking discovery was made possible by combining multiple observations and applying advanced statistical techniques to the data. The detection of water on K218b is particularly exciting because the planet resides in the habitable zone of its star, where temperatures could potentially support liquid water on the surface. While the presence of water vapor in the atmosphere does not guarantee the existence of liquid water on the planet's surface, it marks a significant step in our search for potentially habitable worlds beyond our solar system. This finding opens up new possibilities for understanding the diversity of exoplanets and the potential for life elsewhere in the universe. K218b, an exoplanet that has captured the attention of astronomers, could have a significant portion of its mass composed of water. Current estimates suggest that up to 30% of this distant world's mass might be water. This is a staggering amount when compared to Earth, where water makes up less than 1% of our planet's mass. The abundance of water on K218b has led scientists to classify it as a potential water world or ocean planet. The high water content of K218b is believed to exist in various forms throughout the planet. Deep in its interior, water might be present as a supercritical fluid, while closer to the surface, it could form a massive global ocean. The uppermost layers of the planet's atmosphere may contain water vapor, contributing to its overall water inventory. This substantial water composition has important implications for the planet's potential habitability. While the presence of liquid water is often considered a key ingredient for life as we know it, the extreme conditions on K218b might make it challenging for life to emerge or thrive. The planet's size and mass suggest it likely has a much thicker atmosphere than Earth, which could create intense pressures at its surface. The presence of water on K218b significantly enhances its potential for hosting life as we know it. This exoplanet, located about 124 light-years from Earth, orbits within the habitable zone of its red dwarf star. Recent observations have revealed strong evidence of water vapor in its atmosphere, a crucial ingredient for life as we understand it. Water acts as a universal solvent, facilitating chemical reactions necessary for biological processes. On K218b, liquid water could provide an environment where complex organic molecules might form and interact, potentially leading to the emergence of simple life forms. The planet's size, estimated to be about twice the diameter of Earth, suggests it might have a rocky core surrounded by a deep ocean, offering a variety of potential habitats. However, the presence of water alone does not guarantee life. Other factors, such as the planet's temperature, atmospheric composition, and protection from harmful stellar radiation, also play crucial roles. K218b's red dwarf host star emits more intense ultraviolet radiation than our Sun, which could pose challenges for life unless the planet has a protective magnetic field or atmospheric layer. While the discovery of water on K218b is exciting, we must remember that our understanding of life is based solely on Earth's examples. The potential for life on this distant world remains an open question, driving further research and fueling our curiosity about the possibilities that exist in the vast cosmos. K218b, an exoplanet discovered in 2015, has captured the attention of astronomers due to its potential for harboring liquid water oceans. This intriguing world, located about 124 light-years from Earth, orbits within the habitable zone of its red dwarf star. Recent studies have revealed the presence of water vapor in K218b's atmosphere, sparking excitement about the possibility of liquid water on its surface. The planet's size and mass suggest it could be a super-Earth or a mini-Neptune with a rocky core surrounded by a thick atmosphere. The temperature and pressure conditions on K218b might allow for the existence of liquid water oceans. However, the planet's atmosphere likely contains a high concentration of hydrogen, which could create a greenhouse effect and potentially make the surface too warm for Earth-like oceans. While the presence of liquid water oceans on K218b remains uncertain, the planet's characteristics make it a prime candidate for further study. Future observations with more advanced telescopes may provide clearer insights into the true nature of this distant world and its potential for hosting liquid water. The water cycle on K218b likely differs significantly from Earth's due to its unique characteristics. K218b is a super-Earth, larger and more massive than our planet, orbiting a red dwarf star. Its atmosphere contains hydrogen, methane, and water vapor, suggesting the presence of a substantial water component. Unlike Earth, K218b experiences more intense stellar radiation on one side, potentially creating a stark temperature difference between its day and night sides. This temperature gradient could drive powerful winds, carrying water vapor from the hot day side to the cooler night side, where it might condense and fall as precipitation. The planet's stronger gravity could affect cloud formation and precipitation patterns. Water droplets might form and fall more rapidly than on Earth, potentially creating more frequent and intense rainfall events. Additionally, the planet's atmosphere might extend higher than Earth's, allowing for a more expansive region where water vapor can circulate and undergo phase changes. Given the planet's composition and temperature range, water on K218b might exist in exotic phases not commonly found on Earth, such as supercritical states. This could lead to unique atmospheric and surface interactions, further distinguishing its water cycle from the familiar processes we observe on our home planet. Water plays a crucial role in the atmospheric composition of K218b, an exoplanet that has captured the attention of astronomers and planetary scientists. This distant world, located about 124 light-years from Earth, is particularly intriguing because it resides in the habitable zone of its star and shows strong evidence of water vapor in its atmosphere. The presence of water vapor in K218b's atmosphere was detected through careful analysis of the planet's spectral signature as it passed in front of its host star. This technique, known as transit spectroscopy, allows scientists to identify the chemical components in a planet's atmosphere based on how they absorb or reflect light. What makes K218b even more fascinating is that it's the first planet outside our solar system with both water vapor and temperatures that could potentially support life as we know it. The water in its atmosphere could exist in various forms, including vapor, liquid, and possibly even exotic high-pressure ice phases, depending on the planet's exact conditions. However, it's important to note that the presence of water doesn't guarantee habitability. K218b is much larger than Earth, classified as a super-Earth or mini-Neptune, and its overall composition and surface conditions remain uncertain. Nevertheless, the confirmed presence of water in its atmosphere marks a significant step in our quest to understand the diversity of worlds beyond our solar system and the potential for life elsewhere in the universe. The presence of water on K218b could significantly influence its geological processes. This exoplanet, located about 124 light-years from Earth, is believed to have a substantial amount of water, potentially existing in various states due to its unique conditions. Water acts as a powerful agent of change on planetary bodies. On K218b, it could drive weathering processes, breaking down and altering surface materials over time. This weathering might create sediments and reshape the planet's landscape, much like rivers and oceans do on Earth. Furthermore, if K218b has a rocky core, the interaction between water and minerals could lead to hydrothermal activity. This process might create environments similar to deep-sea hydrothermal vents on Earth, which are known to support unique ecosystems. Such activity could also contribute to the cycling of elements and compounds between the planet's interior and surface. The movement and distribution of water on K218b could also influence its tectonic processes, if any exist. Water can act as a lubricant, potentially facilitating the movement of crustal plates or other geological structures. Additionally, the weight of large bodies of water could exert pressure on the planet's crust, possibly leading to deformation or other geological changes over time. The presence of water on K218b presents several significant challenges for future exploration. This exoplanet, located about 124 light-years from Earth, has captured the interest of scientists due to its potential habitability. However, the very feature that makes it intriguing also complicates our ability to study and potentially visit it. The water on K218b likely exists in a supercritical state due to the planet's high temperature and pressure. This unusual phase of water behaves like both a liquid and a gas simultaneously, making it difficult to predict how spacecraft or exploration equipment would interact with such an environment. Traditional designs for landers or probes might not function as expected under these conditions. Another challenge is the planet's thick hydrogen-rich atmosphere. While this atmosphere allows for the presence of water, it also creates a greenhouse effect that traps heat, potentially leading to extreme surface temperatures. This intense heat could damage or destroy any equipment sent to explore the planet's surface or lower atmosphere. The sheer distance to K218b poses perhaps the greatest challenge. With current propulsion technology, it would take an unimaginably long time to reach this exoplanet. Developing the means to traverse such vast distances while keeping a spacecraft and its crew operational for the entire journey is a monumental task that far exceeds our current capabilities. K218b has captured the attention of scientists as a promising candidate for potentially hosting life due to several key factors. This exoplanet, located about 124 light-years from Earth, orbits within the habitable zone of its star. This crucial positioning allows for temperatures that could support liquid water on its surface, a fundamental requirement for life as we know it. Recent observations have revealed the presence of water vapor in K218b's atmosphere, a discovery that has significantly bolstered its potential for habitability. The detection of water, combined with its location in the habitable zone, makes K218b one of the most intriguing exoplanets discovered to date. Furthermore, K218b is classified as a super-Earth, meaning it is larger than our home planet, but smaller than ice giants like Neptune. This size suggests it could have a rocky core, potentially similar to Earth's composition. The planet's mass and radius indicate it might have a substantial atmosphere, which could protect any potential life forms from harmful radiation. While these factors make K218b an exciting subject for further study, it is important to note that the presence of these conditions does not guarantee the existence of life. The planet's larger size means it likely has a much stronger gravitational pull than Earth, which could create a very different environment from what we are familiar with. Nonetheless, K218b remains a prime target for future observations and a beacon of hope in our search for potentially habitable worlds beyond our solar system. Scientists use specific criteria when defining habitability for exoplanets. The primary focus is on the potential for liquid water to exist on the planet's surface, as water is crucial for life as we know it. This concept is often referred to as the habitable zone or Goldilocks zone, where conditions are just right for liquid water. Temperature plays a key role in habitability. A planet must orbit its star at a distance that allows its surface temperature to support liquid water. Too close, and water would evaporate. Too far, and it would freeze. The size and type of the host star also influence this zone, as different stars emit varying amounts of energy. Beyond water, scientists consider other factors. The planet's size and mass are important, as they affect its ability to retain an atmosphere. A suitable atmosphere can provide protection from harmful radiation and help regulate surface temperatures. The presence of a magnetic field is another consideration, as it shields the planet from stellar wind and cosmic rays. Geological activity is also part of the habitability equation. Plate tectonics and volcanic activity can help regulate a planet's carbon cycle, which is crucial for long-term climate stability. While these factors don't guarantee the presence of life, they create conditions where life as we understand it could potentially thrive. The search for habitable planets beyond Earth focuses on several crucial factors. First and foremost is the presence of liquid water, a vital ingredient for life as we know it. This requires a planet to orbit within the habitable zone of its star, where temperatures allow water to exist in liquid form on the surface. The size and composition of a planet also play significant roles in habitability. Planets similar in size to Earth are more likely to retain an atmosphere and have the right gravity for life to thrive. Rocky planets with a solid surface offer a stable environment for potential life forms to evolve and develop. An atmosphere is another critical component. It protects the planet's surface from harmful radiation and helps regulate temperature. The presence of certain gases, such as oxygen and carbon dioxide, can indicate the potential for life or conditions that could support it. Lastly, a stable planetary system is essential. Extreme variations in a planet's orbit or axis tilt can lead to dramatic climate shifts, making it difficult for life to persist. Neighboring planets, particularly gas giants, can provide protection from asteroid impacts, further enhancing a planet's habitability potential. K218b is a fascinating exoplanet that has captured the attention of astronomers and astrobiologists alike. This super-Earth, located about 124 light-years away from us, orbits within the habitable zone of its red dwarf star. The habitable zone is the region around a star where conditions might be right for liquid water to exist on a planet's surface, a key factor in our search for potentially habitable worlds. One of the most exciting aspects of K218b is its atmosphere. Recent observations have revealed the presence of water vapor, suggesting that this planet might have a substantial water content. This discovery is significant because water is considered essential for life as we know it. Additionally, the planet's size and mass indicate that it could potentially retain an atmosphere, another crucial element for habitability. However, it's important to note that while K218b meets some habitability criteria, it also faces challenges. Its proximity to its star means it likely experiences intense radiation, which could be harmful to life forms. The planet's larger size compared to Earth also suggests it might have a much denser atmosphere and higher surface pressure, creating conditions quite different from those we're familiar with on our home planet. Despite these uncertainties, K218b remains a prime candidate for further study in our quest to understand the potential for life beyond Earth. Its combination of size, location, and atmospheric composition makes it a valuable target for future observations and a stepping stone in our exploration of potentially habitable worlds in the cosmos. K218b, an exoplanet located about 124 light-years from Earth, has captured the imagination of scientists and space enthusiasts alike. This super-Earth, significantly larger than our home planet, orbits within the habitable zone of its red dwarf star. Recent observations have revealed the presence of water vapor in its atmosphere, sparking intense speculation about its potential to harbor life. Given the planet's size and composition, any life forms on K218b would likely be quite different from those we're familiar with on Earth. The planet's stronger gravity could result in organisms with flatter, more spread-out body structures. If there's a substantial ocean, we might find creatures adapted to high-pressure aquatic environments, possibly resembling some of Earth's deep-sea organisms. The atmosphere of K218b, rich in hydrogen and helium, presents both challenges and opportunities for potential life. While these conditions differ greatly from Earth's oxygen-rich air, some scientists propose that microbial life could potentially evolve to use hydrogen as an energy source. Such organisms might float in the planet's upper atmosphere, where temperatures and pressures are more moderate. However, it's crucial to temper our expectations. The presence of water and a position in the habitable zone doesn't guarantee life. Factors such as the planet's magnetic field strength, its ability to shield the surface from intense stellar radiation, and the stability of its atmosphere over long periods all play critical roles in determining whether K218b could truly support life as we know it, or perhaps life as we don't yet know it. Life on K218b, an exoplanet about 8 times the mass of Earth, could be vastly different from what we know on our homeworld. The planet orbits a red dwarf star and lies within the habitable zone, where liquid water could exist on its surface. However, the conditions there would be far from Earth-like. The intense gravity on K218b would likely result in a much denser atmosphere than Earth's. This could lead to potential life forms evolving to withstand high pressures. They might develop thick, sturdy body structures or remain small to cope with the gravitational forces. The atmosphere might also contain a high concentration of hydrogen, which could give rise to unique biochemistries we have not encountered before. The radiation environment around K218b would be another significant factor. Red dwarf stars are known for their frequent and intense flares, bombarding their planets with high-energy particles. Any life on K218b would need robust mechanisms to protect against this radiation, perhaps through advanced cellular repair systems or by living underground or underwater. Given the different light spectrum emitted by the red dwarf star, photosynthesis as we know it might not be possible. Life forms could evolve alternative energy harvesting methods, possibly using infrared light or chemical energy from the planet's interior. This could result in alien ecosystems with no resemblance to the green landscapes of Earth, presenting us with truly otherworldly sights if we could ever observe them. K218b presents several significant challenges for potential life forms. The exoplanet orbits a red dwarf star, which emits intense radiation and frequent stellar flares. These conditions could be harmful to any life on the planet's surface, potentially damaging organic molecules and disrupting biological processes. The planet's size and mass suggest it might be a mini Neptune rather than a rocky world like Earth. This means it could have a thick hydrogen and helium atmosphere, making the surface pressure extremely high. Such pressure would be inhospitable for life as we know it, possibly crushing complex organisms. Temperature is another crucial factor. While K218b is within its star's habitable zone, its actual surface temperature remains uncertain. Depending on its atmospheric composition, the planet could be too hot or too cold for liquid water to exist on its surface, a key ingredient for life as we understand it. Lastly, the planet's potential high gravity, due to its larger size compared to Earth, could pose challenges for the development of complex life forms. It might restrict the size and mobility of any organisms that could theoretically evolve there, limiting the potential for diverse ecosystems. K218b, an exoplanet about twice the size of Earth, orbits a red dwarf star in its habitable zone. This positioning raises intriguing questions about its potential to host life. However, the radiation environment of K218b presents significant challenges for any hypothetical organisms. Red dwarf stars, while smaller and cooler than our Sun, are known for their volatile nature. They frequently emit powerful flares and intense ultraviolet radiation. K218b, being closer to its star than Earth is to the Sun, likely receives a much higher dose of this harmful radiation. This increased exposure could potentially strip away the planet's atmosphere over time, leaving its surface unprotected. The intense radiation might also pose direct threats to any life forms on the planet's surface. High-energy particles and ultraviolet light can damage organic molecules and disrupt cellular processes. However, it's worth noting that life is remarkably adaptable. Some organisms on Earth have evolved mechanisms to repair radiation damage or even thrive in high-radiation environments. Despite these challenges, K218b's potential thick atmosphere and possible ocean could provide some protection from stellar radiation. If life exists there, it might have evolved unique strategies to cope with the harsh radiation environment, perhaps thriving in underground habitats or deep oceans where radiation penetration is limited. The study of K218b's radiation environment continues to fascinate scientists as they explore the possibilities for life beyond our solar system. Temperature plays a crucial role in determining a planet's habitability. For life as we know it to exist, a planet must maintain temperatures that allow for liquid water on its surface. This range, often called the habitable zone or Goldilocks zone, varies depending on factors like the planet's atmosphere and its host star's characteristics. A planet's temperature affects numerous processes essential for life. It influences the chemical reactions that can occur, the stability of organic molecules, and the ability of organisms to maintain their internal functions. Too cold, and chemical processes slow down, potentially freezing water and halting biological activities. Too hot, and complex molecules break down, making it difficult for life to form or persist. Temperature also impacts a planet's atmosphere and climate systems. Extreme temperatures can lead to the loss of atmosphere through processes like thermal escape, where lightweight molecules gain enough energy to overcome the planet's gravity. This loss can further alter the planet's ability to maintain stable temperatures and protect potential life from harmful radiation. Moreover, temperature gradients drive weather patterns and ocean currents, which are vital for distributing nutrients and energy across a planet's surface. These processes can create diverse environments and microclimates, potentially increasing the range of habitable niches for different forms of life. The gravity on K218b would significantly influence any potential life forms that might exist there. This super-Earth exoplanet, discovered in 2015, is about 8 times more massive than Earth. As a result, its surface gravity is likely to be much stronger than what we experience on our home planet. This increased gravitational pull would have profound effects on the development and characteristics of any life that might evolve on K218b. Organisms would need to adapt to the higher gravity by developing stronger muscles and more robust skeletal structures. They might evolve to be shorter and stockier than their Earth counterparts to better withstand the gravitational forces. The stronger gravity could also affect the planet's atmosphere, potentially making it denser and more compressed. This could impact the size and shape of any flying creatures that might evolve, as they would need to generate more lift to overcome the stronger gravitational pull. Aquatic life, if present, might face less of a challenge, as the buoyancy of water would help counteract some of the effects of increased gravity. Plant life, too, would be affected. Vegetation might grow lower to the ground and develop thicker, stronger stems to support their weight against the heightened gravitational force. The circulation of fluids within these organisms would also need to adapt to overcome the stronger downward pull. Overall, the gravity on K218b would be a major factor shaping the potential evolution and characteristics of any life forms that might exist there. K218b, an intriguing exoplanet that has captured the attention of astronomers, was initially discovered using the Kepler Space Telescope during its extended K2 mission. This powerful space-based observatory detected the planet by observing periodic dips in the brightness of its host star, a method known as the transit technique. Following its discovery, researchers employed the Hubble Space Telescope to conduct a more detailed study of K218b. Hubble's sensitive instruments allowed scientists to analyze the planet's atmosphere by examining the starlight that passed through it during transits. This technique, called transmission spectroscopy, provided crucial information about the composition of K218b's atmosphere. Ground-based telescopes also played a role in studying this distant world. The HARPS spectrograph at the European Southern Observatory's La Silla facility in Chile helped determine the planet's mass by measuring tiny wobbles in the motion of its host star. Additionally, the United Kingdom Infrared Telescope in Hawaii contributed to refining our understanding of the star's properties, which in turn helped characterize the planet more accurately. The combined efforts of these telescopes, from space-based observatories to ground-based instruments, have provided a wealth of information about K2-18b, making it one of the most promising candidates for potentially habitable worlds beyond our solar system. The transit method is a powerful technique astronomers use to discover planets orbiting distant stars. This method relies on detecting the tiny dip in a star's brightness that occurs when a planet passes in front of it, as seen from Earth. When a planet transits its star, it blocks a small fraction of the star's light from reaching us. This causes a periodic dimming of the star's overall brightness. By carefully measuring these regular dips in brightness, scientists can not only confirm the presence of a planet, but also gather valuable information about its size and orbit. The amount of light blocked during a transit depends on the size of the planet relative to its star. A larger planet will block more light, causing a more noticeable dip in brightness. By analyzing the depth of these dips, astronomers can estimate the planet's size. The time between transits reveals the length of the planet's year, or how long it takes to complete one orbit around its star. This method has proven incredibly successful, leading to the discovery of thousands of exoplanets. It works best for detecting large planets orbiting close to their stars, as these create more noticeable and frequent dips in brightness. However, with increasingly sensitive instruments, even smaller Earth-sized planets are now being found using the transit method. Spectroscopy is a powerful technique used by astronomers to analyze the light from distant celestial objects. It involves splitting light into its component colors, much like a prism creates a rainbow. This spectrum of light can reveal a wealth of information about an object's composition, temperature, and even motion. In the case of K2-18b, an exoplanet about 124 light-years from Earth, spectroscopy played a crucial role in uncovering its potential habitability. Scientists used the Hubble Space Telescope to observe K2-18b as it passed in front of its host star. During these transits, some of the starlight filtered through the planet's atmosphere. By analyzing the spectrum of this filtered light, researchers detected the signature of water vapor in K2-18b's atmosphere. This discovery was groundbreaking, as it marked the first time water vapor was detected in the atmosphere of an exoplanet within the habitable zone of its star. Furthermore, spectroscopic analysis suggested the presence of hydrogen and helium in K2-18b's atmosphere, providing insights into the planet's overall composition and structure. These findings have significantly advanced our understanding of potentially habitable worlds beyond our solar system and demonstrated the power of spectroscopy in exoplanet research. The Hubble Space Telescope played a crucial role in the groundbreaking research of K2-18b, an exoplanet that has captured the attention of astronomers worldwide. This powerful space observatory, orbiting high above Earth's atmosphere, provided scientists with invaluable data about the planet's atmosphere. In 2019, researchers used Hubble's Wide Field Camera 3 to analyze the light passing through K2-18b's atmosphere as the planet transited its host star. This technique, known as transmission spectroscopy, allowed scientists to detect the presence of water vapor in the planet's atmosphere. This discovery marked the first time water vapor was detected in the atmosphere of an exoplanet within the habitable zone of its star. Hubble's observations also helped researchers estimate the planet's size and mass, confirming that K2-18b is a super-Earth, larger than our home planet, but smaller than ice giants like Neptune. The telescope's data suggested that K2-18b might have a substantial hydrogen-rich atmosphere, which could potentially harbor clouds where liquid water droplets form. While Hubble's findings were exciting, they also highlighted the need for more advanced instruments to study exoplanets in greater detail. This paved the way for future missions, such as the James Webb Space Telescope, to build upon Hubble's pioneering work and further our understanding of potentially habitable worlds beyond our solar system. Scientists employ several sophisticated techniques to determine the composition of an exoplanet's atmosphere, with one of the most powerful methods being transit spectroscopy. When an exoplanet passes in front of its host star, some of the starlight filters through the planet's atmosphere. Different gases in the atmosphere absorb specific wavelengths of light, creating a unique spectral fingerprint. By analyzing this spectral data, astronomers can identify the presence of various molecules and elements in the exoplanet's atmosphere. For example, they might detect water vapor, methane, carbon dioxide, or even exotic compounds like titanium oxide. This method works particularly well for large, gaseous planets orbiting close to their stars, as they provide more atmospheric material for light to pass through. Another technique scientists use is called emission spectroscopy. This method involves observing the planet when it passes behind its star, allowing researchers to measure the difference in light emitted by the star alone versus the star and planet combined. This helps determine the planet's temperature and can provide clues about its atmospheric composition. Advancements in technology, such as the James Webb Space Telescope, are significantly enhancing our ability to study exoplanet atmospheres. These powerful instruments allow scientists to gather more detailed spectral data, potentially revealing the presence of biomarkers that could indicate the possibility of life on distant worlds. Astronomers are constantly pushing the boundaries of technology to study distant worlds like K218b. One exciting development is the use of advanced spectrographs, which can analyze the light passing through an exoplanet's atmosphere with unprecedented precision. These instruments allow scientists to detect the chemical signatures of various elements and compounds, potentially revealing signs of habitability or even life. Another promising technology is the development of star shades, massive flower-shaped structures designed to block out the light from a star, making it easier to directly observe orbiting planets. When paired with powerful space telescopes, star shades could revolutionize our ability to study exoplanets in detail. Adaptive optics systems are also evolving rapidly, using deformable mirrors to counteract the distorting effects of Earth's atmosphere. This technology allows ground-based telescopes to capture sharper images of distant planets, rivaling the clarity of space-based observations. Furthermore, machine learning algorithms are becoming increasingly sophisticated, helping astronomers sift through vast amounts of data to identify promising exoplanet candidates and extract valuable information about their properties. These AI-powered tools are accelerating the pace of discovery and enabling more comprehensive studies of worlds like K218b. Computer models play a crucial role in our understanding of exoplanets like K218b, allowing scientists to simulate and analyze conditions that are impossible to observe directly. These sophisticated digital tools combine data from telescopes and theoretical physics to create virtual representations of distant worlds. For K218b, computer models help researchers explore the planet's potential atmosphere and internal structure. By inputting known information such as the planet's size, mass, and orbital characteristics, scientists can generate simulations of its possible compositions. These models consider various scenarios, from a rocky super-Earth to a mini Neptune with a substantial gaseous envelope. One of the most exciting applications of computer modeling for K218b is in the study of its potential habitability. Models can simulate the planet's climate, taking into account factors like its distance from its star, atmospheric composition, and potential water cycle. This allows scientists to estimate surface temperatures and pressures, helping determine if liquid water could exist on the planet's surface. Furthermore, these digital simulations assist in planning future observations. By predicting which atmospheric components might be detectable, computer models guide astronomers in choosing the most effective instruments and observation strategies for further study of K218b and similar exoplanets. Studying distant exoplanets presents significant challenges for astronomers. Our current methods, while advanced, still face substantial limitations. The primary obstacle is the vast distances involved. Even the closest exoplanets are light years away, making direct observation extremely difficult. One common technique, the transit method, relies on detecting minute dips in a star's brightness as a planet passes in front of it. However, this method only works for planets whose orbits align perfectly with our line of sight, meaning we miss many potential worlds. Additionally, Smaller planets or those orbiting larger stars produce such tiny dips that they can be easily overlooked. Another approach, the radial velocity method, measures the slight wobble of a star caused by an orbiting planet's gravitational pull. This technique is biased towards finding large planets close to their stars, as these create more noticeable wobbles. Consequently, many Earth-sized planets in habitable zones remain undetected. Direct imaging of exoplanets is perhaps the most challenging method. The glare from a planet's host star typically overwhelms the faint light reflected by the planet itself. While we have made progress in this area, our ability to directly observe smaller Earth-like planets remains limited. These constraints mean our current picture of exoplanet populations is incomplete, potentially skewing our understanding of planetary system formation and the prevalence of habitable worlds in the universe. Scientists employ several methods to account for uncertainties in their measurements of exoplanets like K2-18b. One key approach is using multiple observation techniques and instruments to cross-validate findings. For instance, they might combine data from space telescopes like Hubble with ground-based observatories to build a more comprehensive picture. Statistical analysis plays a crucial role in quantifying uncertainties. Researchers use sophisticated models to process raw data, accounting for factors such as instrument noise and atmospheric interference. These models help establish confidence intervals, indicating the range within which true values likely fall. Repeated observations over time also help refine measurements. As technology improves and more data accumulates, scientists can update their estimates, gradually narrowing the margins of error. This iterative process is essential in exoplanet research, where initial discoveries often come with significant uncertainties. Collaboration within the scientific community further enhances accuracy. By sharing data and methodologies, researchers can identify potential biases or errors in individual studies. This peer review process helps ensure that published results reflect the most reliable current understanding of K2-18b and similar exoplanets. Future missions and advanced instruments will play a crucial role in unraveling the mysteries of K2-18b. The James Webb Space Telescope, with its powerful infrared capabilities, will be able to analyze the atmosphere of this intriguing exoplanet in unprecedented detail. By studying the chemical composition and structure of K2-18b's atmosphere, scientists hope to gain insights into its potential habitability and the presence of biosignatures. Ground-based observatories equipped with next-generation adaptive optics systems will also contribute to our understanding of K2-18b. These advanced technologies will allow astronomers to obtain clearer, more precise measurements of the planet's mass, radius, and orbital characteristics, refining our knowledge of its physical properties. Proposed space missions like the Large Ultraviolet Optical Infrared Surveyor or the Habitable Exoplanet Observatory could provide even more detailed observations of K2-18b and similar exoplanets. These missions aim to directly image distant worlds and analyze their atmospheres, potentially revealing the presence of water, organic molecules, or other indicators of habitability. As our observational capabilities continue to advance, we may also develop new techniques for detecting and studying exoplanets. These could include methods for measuring magnetic fields, analyzing surface features, or even detecting signs of technological civilizations, should they exist. Each new instrument and mission brings us closer to understanding the true nature of K2-18b and its potential to harbor life. K2-18b stands out among potentially habitable exoplanets due to its unique characteristics. This super-Earth, discovered in 2015, orbits a red dwarf star about 111 light-years from Earth in the constellation Leo. What makes K2-18b particularly intriguing is the detection of water vapor in its atmosphere, a crucial ingredient for life as we know it. Compared to other known potentially habitable worlds, K2-18b is larger and more massive. It has a radius about 2.5 times that of Earth and a mass around 8 times greater. This places it in a category between rocky planets like Earth and gas giants like Neptune. Many other potentially habitable exoplanets are closer in size to Earth, making K2-18b an interesting case study for planetary scientists. The planet's location within its star's habitable zone is another factor that sets it apart. K218b receives about the same amount of radiation from its star as Earth does from the Sun, despite orbiting a much cooler star. This balance could allow for the existence of liquid water on its surface, a key consideration for habitability. However, K218b's potential for supporting life remains uncertain. Its larger size suggests it might have a thick, hydrogen-rich atmosphere, which could create extreme pressure at the surface. This environment would be quite different from Earth's and could present challenges for the development of life forms similar to those we're familiar with. Nonetheless, K218b remains a prime target for future studies as we continue to explore the diversity of potentially habitable worlds beyond our solar system. Studying exoplanets like K218b offers valuable insights into our own planet Earth and its place in the cosmos. K218b is a super-Earth, larger than our world but smaller than ice giants like Neptune. Its discovery and subsequent observations have expanded our understanding of planetary diversity and potential habitability beyond our solar system. One key lesson from K218b is the importance of atmospheric composition in determining a planet's potential for life. Scientists have detected water vapor in its atmosphere, a crucial ingredient for life as we know it. This finding suggests that Earth-like conditions might exist on worlds very different from our own, broadening our search parameters for habitable planets. K218b also highlights the role of a planet's position in its solar system. Located in its star's habitable zone, where liquid water can exist on the surface, it reminds us how crucial Earth's distance from the Sun is for maintaining our life-sustaining environment. This reinforces the delicate balance required for a planet to support life and underscores the uniqueness of Earth's position. Furthermore, studying K218b and similar exoplanets helps us appreciate Earth's rarity. While we're discovering more potentially habitable worlds, none yet match Earth's perfect combination of size, composition, atmosphere, and orbital characteristics. This perspective enhances our understanding of Earth's special place in the universe and the importance of preserving our planet's delicate ecosystems. K218b stands out from the gas giants in our solar system in several intriguing ways. Unlike Jupiter and Saturn, which are primarily composed of hydrogen and helium, K218b is believed to have a substantial amount of water in its atmosphere and possibly even a water ocean beneath its gaseous layer. This exoplanet, located about 124 light-years away from Earth, is classified as a super-Earth or mini-Neptune, falling between the size of our planet and Neptune. The atmosphere of K218b contains significant amounts of methane and carbon dioxide, along with water vapor, creating a unique chemical composition not seen in our solar system's gas giants. Its size, estimated to be about 2.5 times the radius of Earth, makes it much smaller than Jupiter or Saturn, yet larger than the ice giants Uranus and Neptune. Another key difference is K218b's proximity to its host star. It orbits within the habitable zone of its cool dwarf star, completing an orbit in just 33 days. This places it much closer to its star than any of our gas giants are to the Sun, resulting in temperatures that could potentially support liquid water on its surface or in its atmosphere. The discovery of water vapor in the atmosphere of K218b has excited scientists, as it represents one of the first detections of water on a potentially habitable exoplanet. This characteristic sets it apart from our solar system's gas giants and opens up new possibilities in the search for worlds that could potentially harbor life. K218b, a distant exoplanet discovered in 2015, shares some intriguing similarities with our neighboring planets Venus and Mars, while also possessing unique characteristics that set it apart. Like Venus and Mars, K218b orbits within its star's habitable zone, the region where conditions might allow for liquid water on a planet's surface. This placement makes it a subject of great interest in the search for potentially habitable worlds beyond our solar system. In terms of size, K218b is significantly larger than both Venus and Mars, classified as a super-Earth or mini-Neptune. Its mass is estimated to be about 8 times that of Earth, placing it between our rocky homeworld and the ice giants of our outer solar system. This size difference means that K218b likely has a much thicker atmosphere than either Venus or Mars, potentially creating a greenhouse effect similar to what we observe on Venus. Recent studies have suggested that K218b might have a hydrogen-rich atmosphere with water vapor, a feature that draws comparisons to the early atmospheres of Venus and Mars before they evolved into their current states. This atmospheric composition could create a water cycle on K218b, reminiscent of Earth's hydrological processes, but under very different conditions. However, unlike Venus and Mars, K218b orbits a red dwarf star, which is cooler and smaller than our Sun. This means the planet receives a different spectrum and intensity of radiation, potentially affecting its climate and habitability in ways we are still working to understand. The study of K218b and its similarities to Venus and Mars provides valuable insights into the diversity of planetary environments and the potential for life beyond our solar system. K218b's formation history likely diverges significantly from Earth's due to its unique characteristics and location. This exoplanet, discovered in 2015, orbits a red dwarf star approximately 124 light-years from Earth. Unlike our home planet, K218b is classified as a sub-Neptune, with a mass roughly 8 times that of Earth and a radius about 2.5 times larger. The formation process of K218b probably began in a similar manner to Earth, with the accumulation of rocky material in the protoplanetary disk surrounding its young star. However, its greater mass allowed it to attract and retain a substantial gaseous envelope, primarily composed of hydrogen and helium. This key difference sets it apart from Earth, which lacks such an extensive primordial atmosphere. Another crucial factor in K218b's formation is its position within its star system. Located in the habitable zone of its cooler red dwarf star, K218b receives levels of radiation comparable to Earth. This placement likely influenced its development, potentially allowing it to retain water in liquid form on its surface or within its atmosphere. The intense gravity and pressure conditions on K218b, resulting from its larger size, would have shaped its internal structure differently from Earth's. While Earth has a distinct core, mantle, and crust, K218b might have a more complex layered structure, possibly including a rocky core surrounded by high-pressure ice layers and a thick gaseous envelope. K218b offers a fascinating glimpse into the incredible variety of planets that exist beyond our solar system. This exoplanet, located about 124 light-years from Earth, challenges our traditional understanding of planetary categories. It falls into a class known as super-Earths or mini-Neptunes, being larger than Earth but smaller than Neptune. What makes K218b particularly intriguing is its potential habitability. The planet orbits within the habitable zone of its star, where temperatures could allow for liquid water on the surface. Moreover, observations have detected water vapor in its atmosphere, along with hydrogen and helium. This combination suggests K218b might have a substantial water ocean beneath a hydrogen-rich atmosphere. The existence of K218b demonstrates that planets can form and exist in configurations quite different from those in our solar system. It shows that potentially habitable worlds can come in sizes and compositions we do not see locally, expanding our search parameters for life-supporting planets. The planet's discovery and subsequent studies highlight the importance of considering a wider range of planetary types when looking for potentially habitable worlds. K218b serves as a reminder of the vast diversity in planetary systems across the universe. It underscores the need for continued exploration and study of exoplanets, as each new discovery has the potential to reshape our understanding of planetary formation, evolution, and the conditions that might support life beyond Earth. K218b challenges our traditional understanding of planetary classification by blurring the lines between what we typically consider a super-Earth and a mini-Neptune. This exoplanet, located about 124 light-years away from Earth, has a mass and size that place it in a curious middle ground between these two categories. With a radius about 2.5 times that of Earth and a mass about 8 times greater, K218b falls into what scientists call the transition regime. This is a range where planets could be either rocky super-Earths or gaseous mini-Neptunes. What makes K218b particularly intriguing is the recent detection of water vapor in its atmosphere, along with the potential presence of liquid water clouds. This discovery challenges our expectations because planets of this size were generally thought to have thick hydrogen and helium atmospheres, making them more akin to gas giants than rocky worlds. The presence of water in the atmosphere of K218b suggests that it might have a more complex composition than previously assumed for planets in this size range. Furthermore, K218b orbits within the habitable zone of its star, where temperatures could allow for liquid water to exist on a planetary surface. This combination of size, composition, and orbital characteristics forces us to reconsider our definitions of potentially habitable worlds and expand our search criteria for life-supporting planets beyond those that closely resemble Earth. K218b offers a fascinating glimpse into the diverse nature of exoplanets and the potential for habitable worlds beyond our solar system. This super-Earth, located about 124 light-years away in the constellation Leo, orbits a red dwarf star in what scientists call the habitable zone. Its discovery and subsequent observations have provided valuable insights into planetary formation and evolution. The existence of K218b challenges our understanding of how planets form and develop over time. Its size, roughly 2.5 times that of Earth, places it in a category between rocky terrestrial planets and gas giants. This intermediate size suggests that super-Earths like K218b might represent a crucial stage in planetary evolution, potentially bridging the gap between smaller rocky worlds and larger gaseous ones. Perhaps most intriguingly, K218b has an atmosphere containing significant amounts of water vapor. This discovery marks the first time water vapor has been detected in the atmosphere of an exoplanet within the habitable zone. Such findings hint at the possibility that water-bearing worlds might be more common in the universe than previously thought, expanding our search parameters for potentially habitable planets. Moreover, the study of K218b and similar exoplanets is reshaping our theories about planetary migration. The planet's current orbit may not be where it originally formed, suggesting that planetary systems can undergo significant changes over time. This dynamic view of planetary evolution opens up new avenues for understanding the diversity of exoplanets we observe and the potential for life-supporting conditions to develop in unexpected places across the cosmos. Studying K218b offers valuable insights into the nature of super-Earths, a class of planets that are larger than Earth but smaller than Neptune. These planets are common in our galaxy, yet absent in our solar system, making them intriguing subjects for exoplanet research. K218b is particularly significant because it orbits within its star's habitable zone and has an atmosphere containing water vapor. This combination makes it one of the most promising candidates for potentially habitable worlds beyond our solar system. By analyzing its atmosphere and composition, scientists can better understand the conditions that might support life on planets larger than Earth. The study of K218b also helps refine our models of planetary formation and evolution. Its size and orbit challenge some existing theories about how and where such planets form, prompting scientists to revise their understanding of planetary systems. This, in turn, informs our search for other potentially habitable worlds. Furthermore, the techniques developed to study K218b pave the way for future observations of similar planets. As our instruments and methods improve, we can apply these lessons to investigate other super-Earths, gradually building a more comprehensive picture of these fascinating worlds and their potential for hosting life. The study of K218b has provided valuable insights that will shape future exoplanet research. This distant world, located about 124 light-years from Earth, has taught us the importance of looking beyond the traditional habitable zone when searching for potentially life-supporting planets. K218b falls into a category called sub-Neptunes or mini-Neptunes, which are more common in the galaxy than Earth-like rocky planets. The detection of water vapor in its atmosphere has expanded our understanding of where we might find the ingredients for life. This discovery emphasizes the need to broaden our search criteria and consider a wider range of planetary types and conditions. The research techniques used to study K218b have also proven crucial. The combination of transit spectroscopy and atmospheric modeling has shown how we can glean significant information about a planet's composition and potential habitability, even from great distances. These methods will undoubtedly be refined and applied to future exoplanet studies, allowing us to build a more comprehensive picture of worlds beyond our solar system. Perhaps most importantly, K218b has reinforced the idea that our galaxy is diverse and full of surprises. As we continue to explore, we must remain open-minded about what constitutes a habitable world and be prepared to challenge our preconceptions about where life might exist in the universe. Studying distant planets presents numerous challenges for astronomers and planetary scientists. The vast distances involved make direct observation extremely difficult. Even our most powerful telescopes struggle to capture clear images of planets beyond our solar system. Instead, scientists often rely on indirect methods to gather information. One major obstacle is the faintness of light from these faraway worlds. As light travels enormous distances through space, it becomes incredibly dim, making it hard to detect and analyze. This problem is compounded by the fact that planets do not produce their own light, but merely reflect light from their parent stars. Separating this faint planetary light from the overwhelming glare of the star is a formidable task. Time is another significant factor. Many of the techniques used to study distant planets require long observation periods, sometimes spanning months or even years. This is necessary to detect subtle changes or patterns that might reveal information about the planet's orbit, composition, or atmosphere. Furthermore, the vast distances mean that the light we observe from these planets is actually quite old, having taken many years to reach us. This time delay can complicate our understanding of current conditions on these worlds. Lastly, the limitations of our current technology pose significant challenges. While our instruments are constantly improving, they are still not advanced enough to provide detailed information about many aspects of distant planets. Features like surface conditions, weather patterns, or potential signs of life remain frustratingly out of reach for all but the closest and largest planets. Despite these difficulties, scientists continue to develop innovative methods and technologies to expand our knowledge of these far-off worlds. Scientists face significant challenges when studying distant exoplanets like K218b, but they employ a range of innovative techniques to overcome these obstacles. One key method is the use of powerful space-based telescopes, such as the Hubble Space Telescope and the James Webb Space Telescope. These advanced instruments can detect minute changes in light from distant stars, allowing researchers to infer the presence and characteristics of orbiting planets. Spectroscopy plays a crucial role in analyzing the composition of exoplanet atmospheres. By examining the way starlight is filtered through a planet's atmosphere during transit, scientists can identify the presence of specific molecules and gases. This technique has been particularly valuable in studying K218b, revealing potential signs of water vapor in its atmosphere. Computer modeling and simulations also help scientists overcome the vast distances involved. By inputting known data about the planet and its star, researchers can create detailed models that predict the planet's structure, composition, and potential habitability. These models are continually refined as new observational data becomes available. Collaboration among international research teams further enhances our ability to study distant worlds. By combining data from multiple observatories and sharing expertise across disciplines, scientists can build a more comprehensive understanding of exoplanets like K218b, despite the enormous distances that separate us from these fascinating worlds. Studying K218b presents significant challenges due to its immense distance from Earth. Our current telescopes and instruments, while advanced, struggle to gather detailed information about this intriguing exoplanet. One major limitation is the difficulty in directly imaging K218b. The planet is too far and too close to its host star for our telescopes to capture a clear, direct image. This means we rely heavily on indirect methods of observation, which provide limited data about the planet's characteristics. Another hurdle is the precision required to analyze the planet's atmosphere. While we have detected water vapor, confirming the presence of other gases or potential biosignatures demands even more sensitive instruments than we currently possess. The James Webb Space Telescope offers improved capabilities, but even its advanced technology faces constraints when probing a planet so distant. Lastly, the time required for light to travel from K218b to Earth limits real-time observations. The data we receive is already years old by the time it reaches us, making it challenging to study any dynamic processes or changes occurring on the planet. These technological limitations underscore the need for continued advancements in space observation equipment to unlock the secrets of worlds like K218b. Earth's atmosphere presents significant challenges for astronomers studying distant exoplanets like K218b. The constant motion and composition of our atmosphere cause distortions and absorptions that can obscure or alter the faint light signals from these faraway worlds. Water vapor in Earth's air absorbs certain wavelengths of light, making it difficult to detect water in exoplanet atmospheres. This interference is particularly problematic when studying K218b, as scientists are keen to understand its potential water content. Turbulence in our atmosphere also causes stars to twinkle, which can complicate precise measurements of the light passing through an exoplanet's atmosphere during transit observations. To overcome these obstacles, astronomers employ various techniques. Space-based telescopes like Hubble and James Webb operate above Earth's atmosphere, providing clearer views of distant worlds. Ground-based observatories use adaptive optics systems to compensate for atmospheric distortions in real time. Additionally, astronomers combine multiple observations and use sophisticated data processing methods to filter out Earth's atmospheric effects. Despite these challenges, Earth-based observations remain crucial in the study of K218b and other exoplanets. By understanding and accounting for our own atmospheric conditions, scientists can more accurately interpret the data they gather about these distant worlds, gradually piecing together a clearer picture of their nature and potential habitability. K218b orbits a red dwarf star, which presents several unique challenges for astronomical observations. Red dwarfs are smaller and cooler than our Sun, emitting most of their light in the infrared spectrum. This means that traditional visible light telescopes are less effective for studying these systems, requiring astronomers to rely more heavily on infrared instruments. The star's low luminosity also makes it difficult to gather enough light for detailed spectroscopic analysis, which is crucial for determining the composition of K218b's atmosphere. Additionally, red dwarfs are known for their high levels of stellar activity, including frequent flares and star spots. These phenomena can interfere with observations, making it challenging to distinguish between the star's activity and potential signals from the planet. Furthermore, the close proximity of K218b to its star complicates efforts to directly image the planet or separate its light from that of the star. This proximity also means that the planet is likely tidally locked, with one side perpetually facing the star, creating extreme temperature differences that are difficult to model and observe. Despite these challenges, the potential for K218b to harbor conditions suitable for life makes it a compelling target for ongoing research, driving the development of new observational techniques and more sensitive instruments. Scientists employ sophisticated techniques to distinguish signals from K218b from the cosmic background noise. One key method is the transit technique, where they observe the slight dimming of the star's light as the planet passes in front of it. This periodic dimming creates a distinctive pattern that stands out from random fluctuations in stellar brightness. To further refine their observations, astronomers use advanced statistical analysis and noise reduction algorithms. These tools help filter out interference from other celestial bodies, atmospheric disturbances, and instrument-related noise. Multiple observations over extended periods also play a crucial role, allowing researchers to identify consistent patterns that indicate the presence of K218b. Spectroscopic analysis is another powerful tool in the scientists' arsenal. By examining the spectrum of light passing through K218b's atmosphere during transit, they can detect specific absorption lines corresponding to different elements and molecules. This spectral fingerprint is unique to the planet and helps distinguish its signal from background noise. Collaborative efforts between multiple observatories and space-based telescopes also contribute to signal verification. By comparing data from various sources, scientists can corroborate their findings and increase confidence in the detected signals from K218b, effectively separating them from the cosmic background noise. Determining the precise size and mass of exoplanets like K218b presents significant challenges for astronomers. The vast distance between Earth and this distant world, which orbits a star about 124 light-years away, makes direct observation extremely difficult. Scientists primarily rely on indirect methods to study K218b. The transit method, which measures the slight dimming of a star's light as a planet passes in front of it, can provide an estimate of the planet's size. However, this technique is subject to uncertainties due to factors such as the star's inherent variability and the presence of stellar spots. Estimating the mass of K218b is even more complex. Astronomers use the radial velocity method, which detects the tiny wobbles in the star's motion caused by the gravitational pull of orbiting planets. This method becomes less precise for smaller, more distant planets and can be affected by the star's own activity and the presence of other planets in the system. Furthermore, the composition of K218b's atmosphere and internal structure can affect calculations of its size and mass. Uncertainties in these factors contribute to the overall challenge of pinpointing the exact physical properties of this intriguing exoplanet, highlighting the ongoing need for more advanced observation techniques and instruments in the field of exoplanet research. Uncertainties in measurements play a crucial role in our understanding of exoplanets like K218b, shaping our knowledge and sometimes leading to revised conclusions. For K218b, a potentially habitable super-Earth about 124 light-years away, these uncertainties have significant implications. The mass and radius of K218b are key parameters, but they come with error margins. These uncertainties affect our estimates of the planet's density and composition. A slightly larger radius or smaller mass could mean the difference between a rocky world with a thin atmosphere and an ocean world with a thick hydrogen envelope. Spectroscopic measurements of K218b's atmosphere also have uncertainties. The detection of water vapor, while exciting, comes with error bars that influence our confidence in the finding. These uncertainties extend to other potential atmospheric components, affecting our understanding of the planet's potential habitability. Temperature estimates for K218b also have margins of error. Even small temperature variations can significantly impact our assessment of whether liquid water could exist on its surface, a crucial factor for potential habitability. As we refine our measurements and reduce uncertainties, our picture of K218b and similar exoplanets will continue to evolve, sometimes in surprising ways. Interpreting data about exoplanets like K218b presents several significant challenges for astronomers and planetary scientists. One major hurdle is the vast distance between Earth and this alien world, which orbits a star about 124 light-years away. This enormous separation means that the data we receive is limited and often requires complex analysis to extract meaningful information. The primary method used to study K218b is transit spectroscopy, which examines how the planet's atmosphere affects starlight as it passes in front of its host star. However, this technique provides only a tiny signal, making it difficult to distinguish between different atmospheric components with certainty. Scientists must carefully account for potential contamination from the star's own atmosphere and other sources of noise in the data. Another challenge lies in the limitations of current technology. While our instruments are incredibly advanced, they still struggle to provide the level of detail needed to definitively characterize the atmosphere of a distant exoplanet. This means that scientists often work with probabilities rather than certainties, leading to ongoing debates about the true nature of K218b's composition and conditions. Furthermore, our understanding of exoplanet formation and evolution is still developing. This makes it challenging to interpret the data within a broader context, as we may be missing key pieces of the puzzle that could help explain the observations. As a result, scientists must remain open to revising their conclusions as new information becomes available and our theoretical models improve. Future technological advancements hold great promise for expanding our understanding of exoplanets like K218b. As our observational capabilities improve, we will be able to gather more detailed information about these distant worlds. One key area of advancement is in space-based telescopes. The James Webb Space Telescope, launched in late 2021, represents a significant leap forward in our ability to study exoplanet atmospheres. Its powerful infrared instruments allow us to detect a wider range of molecules, potentially revealing more about the composition of K218b and similar planets. Another exciting development is the concept of star shades. These large flower-shaped structures could be deployed in space to block out the light from a star, allowing telescopes to directly observe orbiting planets. This technology could provide unprecedented views of exoplanets, potentially allowing us to see surface features and atmospheric patterns on worlds like K218b. Advancements in spectroscopy techniques and data analysis algorithms will also play a crucial role. As these methods become more sophisticated, we will be able to extract more information from the light passing through exoplanet atmospheres, revealing subtler details about their composition and potential habitability. Several space missions in development could significantly enhance our understanding of K218b, a potentially habitable exoplanet that has captured the attention of astronomers worldwide. The James Webb Space Telescope, launched in late 2021, is expected to play a crucial role in studying this intriguing world. With its advanced infrared capabilities, the Webb telescope will be able to analyze the atmosphere of K218b in unprecedented detail, potentially confirming the presence of water vapor and other biomarkers. Another promising mission is the European Space Agency's Ariel spacecraft, scheduled for launch in 2028. Ariel is specifically designed to study the atmospheres of exoplanets, and K218b is likely to be one of its prime targets. This mission could provide valuable data on the planet's chemical composition and atmospheric dynamics. The proposed Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, is a concept for a highly capable space observatory that could launch in the 2030s. If approved and built, LUVOIR would have the power to directly image smaller Earth-like exoplanets and analyze their atmospheres, potentially including K218b. These future missions, working in concert with ground-based observatories, promise to unlock the secrets of K218b and other potentially habitable worlds, bringing us closer to answering the age-old question of whether we are alone in the universe. The James Webb Space Telescope, a powerful space observatory launched in late 2021, is set to revolutionize our understanding of exoplanets like K218b. This remarkable telescope offers unprecedented capabilities to peer into the atmospheres of distant worlds, providing scientists with invaluable data about their composition and potential habitability. For K218b, a planet roughly 8 times the mass of Earth orbiting a red dwarf star, the James Webb Space Telescope can conduct detailed spectroscopic analysis of its atmosphere. This process involves examining the light that passes through the planet's atmosphere as it transits its star, allowing scientists to identify the presence of various molecules and compounds. One of the most exciting prospects is the potential detection of biosignatures, chemical markers that could indicate the presence of life. The James Webb Space Telescope's sensitive instruments might be able to detect molecules such as methane, carbon dioxide, and water vapor in K218b's atmosphere, offering clues about the planet's environmental conditions and possible biological processes. Furthermore, the telescope's advanced capabilities could help determine the planet's temperature, atmospheric pressure, and cloud composition. This wealth of information will significantly enhance our understanding of K218b's overall characteristics and its potential to support life as we know it, marking a significant step forward in our exploration of worlds beyond our solar system. To study K218b in detail, we would need a sophisticated space telescope specifically designed for exoplanet observation. This telescope would need to be significantly more powerful than our current instruments, capable of detecting and analyzing the faint light from distant worlds with unprecedented precision. The mission would likely require a large space-based observatory, possibly with a mirror several times larger than that of the James Webb Space Telescope. This increased size would allow for greater light-gathering capacity and improved resolution, enabling scientists to capture more detailed information about K218b's atmosphere and surface conditions. The telescope would need advanced spectroscopic capabilities to break down the light from K218b into its component wavelengths. This would allow researchers to identify the presence and abundance of various molecules in the planet's atmosphere, potentially including water vapor, methane, and other compounds of interest. Additionally, the mission would benefit from long-duration observations, possibly spanning several years. This extended timeframe would enable scientists to study seasonal variations on K218b, track potential weather patterns, and gather a comprehensive dataset about the planet's characteristics over time. Such a dedicated mission would represent a significant leap forward in our ability to study and understand potentially habitable worlds beyond our solar system. Directly imaging K218b presents significant challenges due to its immense distance from Earth. This exoplanet orbits a red dwarf star approximately 124 light-years away in the constellation Leo. At this vast distance, capturing a clear direct image of K218b is beyond the capabilities of our current telescopes. The primary obstacle in imaging K218b is its proximity to its host star. From our vantage point, the planet appears extremely close to its star, making it difficult to distinguish the faint light of the planet from the overwhelming brightness of the star. This challenge is compounded by the fact that K218b is not a particularly large planet, estimated to be about 2.5 times the size of Earth. While direct imaging of K218b is not currently possible, astronomers have been able to study this exoplanet through other methods, such as transit photometry and spectroscopy. These techniques have allowed scientists to gather valuable information about the planet's size, orbit, and even the composition of its atmosphere. Future advancements in telescope technology, such as the upcoming James Webb Space Telescope and proposed space-based observatories, may bring us closer to directly imaging planets like K218b. However, it will likely be many years or even decades before we can capture a clear, direct image of this distant world. To better study K218b, astronomers need several key technological advancements. First and foremost, more powerful space telescopes are essential. These advanced instruments would allow scientists to capture clearer, more detailed images of the exoplanet and its atmosphere. Improved spectroscopic capabilities are also crucial, as they would enable researchers to analyze the planet's atmospheric composition with greater precision. Enhancing our ability to detect and measure biosignatures is another critical area for advancement. This involves developing more sensitive instruments capable of identifying potential signs of life in K218b's atmosphere. Additionally, improvements in data processing and analysis techniques would help scientists interpret the vast amounts of information collected from these distant observations more effectively. Advancements in propulsion technology are also necessary for future missions that might involve sending probes or spacecraft to study K218b up close. While such missions are currently beyond our capabilities, developing faster and more efficient space travel methods could bring us closer to exploring this intriguing exoplanet in person. Lastly, refining our understanding of planetary formation and evolution through improved computer models and simulations would greatly aid in interpreting the data we gather about K218b. These advancements would help scientists better contextualize their observations and make more accurate predictions about the planet's potential habitability. Machine learning and artificial intelligence are poised to revolutionize our understanding of exoplanets like K218b. These advanced computational tools can sift through vast amounts of data from space telescopes and ground-based observatories, identifying subtle patterns and signals that human researchers might miss. In the case of K218b, AI algorithms could analyze spectroscopic data to detect the presence of specific molecules in the planet's atmosphere with unprecedented accuracy. This could help scientists determine if the exoplanet truly has conditions suitable for life as we know it. Machine learning models could also predict the planet's internal structure and composition based on its mass, radius, and orbital characteristics. Furthermore, AI could assist in creating more sophisticated climate models for K218b, simulating how its atmosphere might behave under various conditions. This could help researchers understand the planet's potential habitability and weather patterns. As we gather more data from future space missions, machine learning algorithms could continuously update and refine our models of K218b, providing increasingly accurate insights into this intriguing world. By automating many aspects of data analysis and modeling, AI and machine learning will allow scientists to focus on interpreting results and formulating new hypotheses about K2-18b and other exoplanets. This synergy between human expertise and artificial intelligence promises to accelerate our exploration of distant worlds and deepen our understanding of the universe. Sending a probe to K2-18b presents significant challenges due to its immense distance from Earth. Located about 124 light-years away, this exoplanet would require revolutionary advancements in propulsion technology to reach within a reasonable time frame. Current spacecraft, like the Voyager probes, would take over 2 million years to travel that far. Even with substantial improvements, a mission to K2-18b would likely span centuries. This extended duration poses complex issues for spacecraft design, power sources, and maintaining communication over vast distances. Despite these hurdles, K2-18b remains an intriguing target for future exploration. Its potential to harbor liquid water and its size, between that of Earth and Neptune, make it a valuable subject for studying planetary formation and potential habitability. As our technology progresses, we might develop new methods for long-distance space travel or remote sensing that could bring K2-18b within reach. While a physical probe to K2-18b is not feasible in the near future, astronomers continue to study this distant world using powerful telescopes and advanced detection methods. These observations provide valuable data about its atmosphere, composition, and potential for supporting life, expanding our understanding of worlds beyond our solar system. Sending a mission to K2-18b with our current technology would be an immense undertaking, requiring a journey of staggering proportions. This exoplanet, discovered in 2015, lies approximately 124 light-years from Earth. To put this distance into perspective, it would take a spacecraft traveling at the speed of our fastest current technology over 2 million years to reach K2-18b. Our most advanced spacecraft, such as the Parker Solar Probe, can achieve speeds of about 430,000 miles per hour. While this might seem incredibly fast, it pales in comparison to the vast distances of interstellar space. Even at this speed, which is far beyond what we could practically achieve for long-distance space travel, the journey would take an unimaginably long time. The challenges of such a mission extend far beyond just the travel time. We would need to develop new propulsion systems, life support technologies, and communication methods capable of spanning the enormous distances involved. Additionally, we would need to address issues such as cosmic radiation protection and the psychological effects of such long-term isolation on any potential crew. Given these limitations, a mission to K2-18b remains firmly in the realm of future possibilities rather than current feasibility. However, ongoing research into advanced propulsion technologies, such as nuclear propulsion or theoretical concepts like warp drives, may one day bring such distant worlds within our reach. To study K2-18b up close, we would need a suite of advanced instruments capable of peering through its atmosphere and analyzing its composition. Spectroscopes would be crucial, allowing us to break down the light passing through the planet's atmosphere and identify its chemical makeup. These instruments could help us detect water vapor, methane, and other potential biosignatures. High-resolution cameras would be essential for capturing detailed images of the planet's surface, if visible through its atmosphere. These could reveal features like cloud patterns, storms, or even surface structures if the atmosphere is thin enough. Infrared cameras would be particularly useful, as they could penetrate cloud layers and provide information about the planet's temperature distribution. Magnetometers would help us understand K2-18b's magnetic field, which could offer insights into its interior structure and potential habitability. Gravity sensors could map the planet's gravitational field, providing clues about its internal composition and the presence of subsurface oceans. Lastly, atmospheric probes designed to withstand the planet's conditions would be invaluable. These could directly sample the atmosphere at different altitudes, measuring pressure, temperature, and composition with unprecedented accuracy. Such instruments would give us the most detailed picture yet of this intriguing exoplanet and its potential to harbor life. Future studies of K2-18b will significantly advance our understanding of potentially habitable exoplanets and refine our search techniques for other life-supporting worlds. As one of the most promising candidates for habitability outside our solar system, K218b offers a unique opportunity to test and improve our methods for detecting signs of life on distant planets. Detailed observations of K218b's atmosphere using next-generation telescopes will allow scientists to search for biosignatures, chemical markers that could indicate the presence of life. By studying how these biosignatures appear in K218b's atmosphere, researchers can develop more accurate models for detecting similar signs on other exoplanets. The exploration of K218b will also help refine our understanding of the habitable zone, the region around a star where conditions could support liquid water on a planet's surface. As a planet larger than Earth but smaller than Neptune, K218b represents a class of planets not found in our solar system. Studying its composition and atmosphere will provide valuable insights into the potential habitability of these super-Earths and mini-Neptunes, which are common throughout the galaxy. Furthermore, the techniques and instruments developed to study K218b will pave the way for more advanced exoplanet observations. These improved methods will enable astronomers to investigate a wider range of planets, increasing our chances of discovering other potentially habitable worlds and ultimately bringing us closer to answering the question of whether we are alone in the universe. The discovery of K218b marks a significant milestone in our quest to understand the cosmos and search for potentially habitable worlds beyond our solar system. This exoplanet, located about 124 light-years from Earth, orbits a red dwarf star in the constellation Leo. What makes K218b particularly intriguing is that it resides within its star's habitable zone and possesses an atmosphere containing water vapor. This finding expands our understanding of planetary diversity and the potential for life-supporting conditions in the universe. K218b is classified as a super-Earth, with a mass about 8 times that of our planet, challenging our previous notions about the types of worlds that might harbor Earth-like conditions. The presence of water vapor in its atmosphere suggests that liquid water could exist on its surface, a key ingredient for life as we know it. Moreover, the discovery of K218b demonstrates the advancing capabilities of our exoplanet detection and analysis technologies. It showcases how we can now probe the atmospheres of distant worlds, opening up new avenues for identifying potential biosignatures on exoplanets. This progress brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? While K218b itself may not be a perfect Earth analog due to its size and the nature of its host star, its discovery fuels optimism about finding more Earth-like planets in the future. It encourages astronomers to focus on similar star systems and refine their search techniques, potentially leading to even more groundbreaking discoveries in our ongoing exploration of the cosmos. K218b offers tantalizing clues about the abundance of potentially habitable worlds in our galaxy. This exoplanet, located about 124 light-years from Earth, orbits within the habitable zone of its red dwarf star. What makes K218b particularly intriguing is the detection of water vapor in its atmosphere, along with hydrogen and helium. The discovery of water on K218b suggests that planets with Earth-like conditions might be more common than previously thought. This finding is significant because water is considered essential for life as we know it. The presence of water vapor in the atmosphere of a planet in the habitable zone raises the possibility that liquid water could exist on its surface, though this remains unconfirmed for K218b. Moreover, K218b is what astronomers call a super-Earth, a type of planet larger than Earth but smaller than Neptune. The prevalence of these super-Earths in other star systems indicates that planets of this size are common in our galaxy. If many of these super-Earths also possess water and orbit within their stars' habitable zones, it could dramatically increase the number of potentially life-supporting worlds. However, it is important to note that while K218b shows promising signs, it is not necessarily a second Earth. Its larger size means it likely has a much denser atmosphere and possibly a rocky core surrounded by a thick layer of ice. Nevertheless, the discovery of water vapor on this distant world encourages astronomers to continue their search for habitable planets, with the hope that worlds similar to our own might be more plentiful than we once imagined. The study of K218b marks a significant milestone in exoplanet research, potentially reshaping our approach to future investigations. This distant world, located about 124 light-years from Earth, has captured the attention of astronomers due to its intriguing characteristics. K218b orbits within the habitable zone of its star, a region where liquid water could potentially exist on a planet's surface. More importantly, observations have detected water vapor in its atmosphere, along with the possibility of clouds. This combination of factors makes K218b one of the most promising candidates for potential habitability outside our solar system. The discovery of these features on K218b is likely to influence future exoplanet research priorities in several ways. Firstly, it may lead to an increased focus on studying the atmospheres of super-Earths and sub-Neptunes, categories to which K218b belongs. These planet types, which do not exist in our solar system, could provide valuable insights into planetary formation and evolution. Furthermore, the study of K218b demonstrates the capabilities of current technology in analyzing exoplanet atmospheres. This success may drive the development of more advanced instruments and techniques, enabling us to examine the atmospheric composition of smaller, more Earth-like planets in the future. As we refine our methods, we move closer to the ultimate goal of identifying potential biosignatures on distant worlds, expanding our search for life beyond Earth. The discovery of potential habitability on K218b opens up a fascinating realm of philosophical questions. This exoplanet, located about 124 light-years away from Earth, has captured the attention of scientists and philosophers alike due to its intriguing characteristics. The presence of water vapor in its atmosphere and its position within the habitable zone of its star forces us to confront our understanding of life in the universe. It challenges our Earth-centric view and raises profound questions about the nature and diversity of life. If life exists on K218b, how different might it be from what we know? This speculation pushes us to expand our definition of life and habitability beyond our terrestrial experiences. Furthermore, the potential for life on K218b prompts us to reconsider our place in the cosmos. Are we unique or just one of many inhabited worlds? This question touches on the core of human exceptionalism and our perceived significance in the universe. It also raises ethical considerations about our responsibilities as potential cosmic neighbors and stewards of life beyond Earth. Lastly, the discovery of K218b and its potential habitability underscores the importance of continued space exploration and scientific inquiry. It reminds us of the vast unknowns that still exist in our universe and the endless possibilities for discovery. This realization can inspire a sense of humility and wonder, encouraging us to approach the cosmos with an open mind and a spirit of exploration. The discovery of K218b has significantly altered our understanding of potentially habitable worlds beyond our solar system. This exoplanet, located about 124 light-years from Earth, orbits a red dwarf star and possesses several intriguing characteristics that challenge our previous notions of what constitutes a habitable world. K218b is notably larger than Earth, falling into a category known as super-Earths. Its size and composition suggest it might have a substantial atmosphere, and remarkably, scientists have detected the presence of water vapor in this atmosphere. This finding marks the first time water vapor has been identified in the atmosphere of an exoplanet within the habitable zone of its star. While Earth has long been considered unique in its ability to support life as we know it, K218b demonstrates that conditions suitable for life might be more common in the universe than previously thought. The presence of water, often considered a key ingredient for life on a planet outside our solar system, expands our understanding of where life could potentially exist. However, it is crucial to note that K218b is not an exact Earth twin. Its larger size and proximity to its star create conditions quite different from those on Earth. Nevertheless, its discovery underscores the diversity of potentially habitable worlds in our galaxy and encourages us to broaden our criteria when searching for signs of life beyond Earth. The discovery of K218b has significant implications for the search for extraterrestrial intelligence. This exoplanet, located about 124 light-years from Earth, orbits within the habitable zone of its star, and possesses characteristics that make it a prime candidate for potential life. K218b is particularly intriguing because it is a super-Earth, larger than our planet but smaller than ice giants like Neptune. What makes it even more exciting is the detection of water vapor in its atmosphere, along with hydrogen and helium. This combination of factors, its size, location in the habitable zone, and the presence of water, makes K218b a compelling target for future SETI efforts. The existence of K218b encourages SETI researchers to expand their search parameters. Traditionally, the focus has been on finding Earth-like planets, but K218b suggests that life might thrive in more diverse environments than previously thought. This could lead to a broadening of the criteria used in identifying potential targets for SETI investigations. Furthermore, K218b serves as a proof of concept for our ability to detect atmospheric compositions of distant exoplanets. As our technology improves, we may be able to detect more complex molecules, including potential biosignatures, in the atmospheres of planets like K218b. This capability could revolutionize our approach to searching for signs of extraterrestrial life and intelligence. K218b has captured the imagination of both scientists and the public, potentially reigniting interest in space exploration. This exoplanet, located about 124 light-years from Earth, orbits within the habitable zone of its star and has shown promising signs of water vapor in its atmosphere. These factors make K218b a tantalizing target for further study and exploration. The discovery of K218b demonstrates the rapid progress in our ability to detect and analyze distant worlds. This advancement could inspire increased funding and support for space missions, both robotic and potentially human-led in the future. The public's fascination with potentially habitable worlds beyond our solar system might drive demand for more advanced telescopes and space-based observatories. Moreover, K218b serves as a concrete example of the diverse planetary systems that exist in our galaxy. This diversity challenges our understanding of planet formation and evolution, encouraging further research and exploration. The possibility of finding signs of life on such distant worlds could motivate young people to pursue careers in astronomy, astrophysics, and related fields. As we continue to learn more about K218b and similar exoplanets, public interest in space exploration is likely to grow. This increased attention could lead to greater support for space agencies and private space companies, potentially accelerating our journey to become a multi-planetary species. The discovery of K218b, an exoplanet that may have conditions suitable for life, could have far-reaching economic implications. This finding might spur increased investment in space exploration and exoplanet research. Governments and private companies could allocate more funds to develop advanced telescopes and spacecraft capable of studying distant worlds in greater detail. The potential for life on K218b could also drive innovation in the field of astrobiology. New technologies and methods for detecting biosignatures from afar might be developed, leading to the creation of specialized instruments and data analysis tools. These advancements could have spillover effects in other industries, such as medical imaging or environmental monitoring. Furthermore, the discovery of K218b might inspire a new generation of scientists and engineers, potentially boosting enrollment in STEM fields. This influx of talent could contribute to technological progress and economic growth across various sectors. The public's fascination with potentially habitable worlds could also fuel growth in space-related tourism and entertainment industries. However, it is important to note that any economic benefits from K218b's discovery are likely to be indirect and long-term. The extreme distance to this exoplanet, over 100 light-years, means that any direct exploitation or visitation is currently beyond our technological capabilities. Nevertheless, the knowledge gained from studying K218b and similar exoplanets could prove invaluable in our understanding of the universe and our place within it. K218b has sparked excitement in the scientific community and reignited discussions about the potential for life beyond Earth. This exoplanet, located about 124 light-years away in the constellation Leo, orbits a red dwarf star and lies within the habitable zone where liquid water could exist on its surface. What makes K218b particularly intriguing is the detection of water vapor in its atmosphere. This discovery, made using data from the Hubble Space Telescope, marks the first time water vapor has been found in the atmosphere of an exoplanet in the habitable zone. The presence of water, often considered a key ingredient for life as we know it, has fueled speculation about the possibility of life-supporting conditions on this distant world. However, K218b is not without its challenges for potential life. Its size and mass suggest it might be a mini Neptune rather than a rocky planet like Earth. This means it could have a thick, hydrogen-rich atmosphere and a high-pressure environment that might not be conducive to life as we understand it. Despite these potential hurdles, the planet's discovery and subsequent observations have provided valuable data for scientists studying the conditions necessary for life to emerge and thrive. The ongoing debate surrounding K218b highlights the complexity of the search for extraterrestrial life. It underscores the need for continued exploration and improved observational techniques to better understand the diverse range of exoplanets in our galaxy and their potential to harbor life. K218b has sparked considerable interest in the scientific community as a potential candidate for future space exploration and colonization discussions. This exoplanet, located about 124 light-years away from Earth, orbits within the habitable zone of its red dwarf star. What makes K218b particularly intriguing is the recent detection of water vapor in its atmosphere. This discovery marks the first time scientists have found water on a planet with temperatures that could potentially support life as we know it. The presence of water, combined with its location in the habitable zone, raises exciting possibilities for the existence of liquid water on its surface. However, it is crucial to temper our enthusiasm with scientific caution. K218b is significantly larger than Earth, with a mass about 8 times greater. This size difference suggests it might be more of a mini Neptune than a rocky planet like Earth. The higher gravity and potentially thick atmosphere could pose significant challenges for any future colonization efforts. Despite these challenges, K218b will likely play a vital role in shaping our understanding of potentially habitable worlds beyond our solar system. It may serve as a valuable case study for developing technologies and strategies for long-distance space travel and colonization. As we continue to study K218b and similar exoplanets, we expand our knowledge of the diverse environments that exist in our galaxy and refine our search for potentially habitable worlds. K218b has captured the attention of astronomers and exoplanet researchers due to its potential for habitability. This super-Earth, located about 124 light-years away in the constellation Leo, orbits within the habitable zone of its red dwarf star. Recent studies have detected water vapor in its atmosphere, a crucial ingredient for life as we know it. The scientific consensus regarding K218b's habitability is cautiously optimistic, but far from definitive. While the planet's location and atmospheric composition are promising, several factors complicate its potential to support life. Its size, estimated to be about 2.5 times that of Earth, suggests it might be a mini Neptune rather than a rocky world. This could mean a thick hydrogen-helium atmosphere unsuitable for Earth-like life. Furthermore, K218b's host star presents challenges. Red dwarfs are known for their volatile nature, often bombarding their planets with intense radiation and stellar flares. This could potentially strip away the planet's atmosphere over time or create conditions hostile to life. Scientists agree that while K218b is an intriguing candidate for further study, more data is needed to determine its true habitability. Future missions and more powerful telescopes will be crucial in unraveling the mysteries of this distant world and assessing its potential to harbor life. K218b has sparked significant interest and debate within the scientific community. This exoplanet, located about 124 light-years from Earth, orbits a red dwarf star in its habitable zone. The primary points of contention revolve around its potential habitability and atmospheric composition. One major debate centers on whether K218b should be classified as a super-Earth or a mini Neptune. Its size and mass place it in a transitional range between these two categories, making precise classification challenging. This uncertainty affects predictions about its surface conditions and potential for hosting life. Another key point of discussion is the planet's atmosphere. While some studies suggest the presence of water vapor, the exact composition and structure of the atmosphere remain unclear. Scientists are debating whether the detected water vapor is part of a substantial atmosphere or if it originates from a hypothetical ocean beneath a thick layer of gases. The potential for life on K218b is perhaps the most contentious topic. Some researchers argue that its position in the habitable zone and the possible presence of water make it a prime candidate for hosting life. Others caution that the planet's size and the intense radiation from its star could create conditions too extreme for life as we know it to exist. These ongoing debates highlight the complexity of exoplanet research and the need for more advanced observational techniques. Research teams analyzing data from K218b have reached varying conclusions, highlighting the complex nature of exoplanet studies. Some scientists interpret the observations as evidence of a potentially habitable world, with signs of water vapor in its atmosphere. These teams suggest K218b might have a rocky core surrounded by a thick layer of water, possibly existing as a global ocean beneath a hydrogen-rich atmosphere. Other researchers are more cautious in their interpretations. They point out that while water vapor has been detected, the planet's size and mass indicate it could be a mini-Neptune rather than a super-Earth. This classification would make it less likely to be habitable in the way we understand it on Earth. These teams emphasize the need for more data to draw definitive conclusions about the planet's composition and potential for habitability. The differences in interpretation stem from the limitations of current observational techniques and the challenges of studying distant worlds. Some teams focus on the potential for life-supporting conditions, while others prioritize a more conservative approach, waiting for more conclusive evidence before making bold claims about habitability. These varying interpretations demonstrate the dynamic nature of exoplanet research and the importance of continued observations and improved technology to refine our understanding of worlds beyond our solar system. As new data becomes available, scientists will continue to debate and refine their models of K218b and similar exoplanets. The exoplanet K218b has captured the attention of astronomers due to its potential for harboring water in its atmosphere. However, several alternative explanations exist for the observations made of this distant world. One possibility is that the signals interpreted as water vapor could be caused by other atmospheric components that produce similar spectral features. Methane or ammonia, for instance, can sometimes mimic the signature of water in certain wavelengths. Another explanation suggests that the planet's atmosphere might be significantly different from initial models. The observed signals could be the result of a thick, hazy atmosphere that scatters light in ways that resemble the presence of water vapor. This scenario would mean that K218b's atmosphere is less Earth-like than some initial interpretations suggested. Some scientists propose that the planet's size and density measurements might be inaccurate due to the limitations of current observational techniques. If K218b is actually smaller or less dense than currently believed, it could have a very different composition and atmospheric structure than what is presently theorized. Lastly, there is the possibility that the observations are affected by activity on the host star. Stellar flares or other phenomena could potentially interfere with the light passing through the planet's atmosphere, leading to misinterpretations of its composition. As with all distant exoplanet observations, continued study and improved technology will be crucial in refining our understanding of K218b and similar worlds beyond our solar system. The discovery of K218b has sparked significant interest and debate within the scientific community. This exoplanet, located about 124 light-years from Earth, has captured attention due to its potential habitability. Astronomers and planetary scientists have responded to claims about K218b with a mix of excitement and caution. Initial observations suggested that K218b orbits within the habitable zone of its star and possesses an atmosphere containing water vapor. This combination of factors led some researchers to propose that the planet could potentially support life. However, the scientific community has been quick to emphasize that the presence of water vapor alone does not guarantee habitability. Many scientists have pointed out that K218b is much larger than Earth, falling into a category known as super-Earths or mini-Neptunes. Its size and mass suggest it might have a thick, hydrogen-rich atmosphere, which could create surface conditions unsuitable for life as we know it. Some researchers argue that the planet's interior could be too hot and pressurized to maintain liquid water on its surface. Despite these challenges, the discovery of K218b has motivated further research and observations. Scientists are developing more advanced techniques and instruments to study exoplanet atmospheres in greater detail. The ongoing debate surrounding K218b highlights the complexity of determining habitability and the need for continued exploration of worlds beyond our solar system. Scientists face several challenges when studying exoplanets like K218b, particularly due to its distance from Earth. Some researchers have questioned the accuracy of atmospheric composition measurements made using transit spectroscopy. This technique analyzes changes in starlight as it passes through a planet's atmosphere, but it can be affected by factors like clouds or haze. Another point of debate centers on the interpretation of data from the Hubble Space Telescope and other instruments. Critics argue that the evidence for water vapor in K218b's atmosphere might not be as conclusive as initially reported. They suggest that alternative explanations for the observed spectral features should be more thoroughly explored. The limited resolution of current telescopes also poses a significant hurdle. Some scientists contend that we need more advanced instruments to make definitive claims about K218b's potential habitability or atmospheric conditions. The James Webb Space Telescope, with its enhanced capabilities, is expected to provide more detailed observations in the future. Lastly, there are concerns about potential biases in the models used to interpret exoplanet data. Some researchers argue that these models may oversimplify complex atmospheric processes, leading to premature conclusions about the nature of distant worlds like K218b. Scientists approach skepticism about K218b's potential for hosting life with a combination of caution and rigorous analysis. They acknowledge that while the exoplanet shows promising characteristics, definitive evidence of life remains elusive. Researchers emphasize the need for further observations and data collection to strengthen or refute the hypothesis of K218b's habitability. One key aspect scientists focus on is the planet's position within its star's habitable zone, where liquid water could exist on the surface. However, they stress that being in this zone alone does not guarantee the presence of life. Atmospheric composition plays a crucial role, and scientists are working to refine their understanding of K218b's atmosphere using advanced telescopes and spectroscopic techniques. To address skeptics, researchers also highlight the importance of considering various forms of life that might exist in conditions different from Earth's. They point out that our understanding of life's requirements is based on a sample size of one, our own planet, and that alien life could potentially thrive in environments we consider inhospitable. Scientists continually refine their models and predictions based on new data, maintaining transparency about the limitations of current knowledge. This open approach helps address skepticism by demonstrating the scientific method in action and showing a willingness to adjust conclusions as new evidence emerges. K218b has sparked significant debate among astronomers and planetary scientists since its discovery. This exoplanet, located about 124 light-years from Earth, orbits a red dwarf star in the habitable zone, making it a tantalizing subject for study. One of the main points of contention is the true nature of K218b. Some researchers argue it could be a super-Earth, a rocky planet larger than our own, but smaller than ice giants. Others contend it is more likely a mini-Neptune with a substantial gaseous envelope. This disagreement stems from uncertainties in the planet's mass and radius measurements, which are crucial for determining its composition and structure. Another hotly debated issue is the potential habitability of K218b. While it orbits in the habitable zone where liquid water could exist on a planetary surface, the planet's size and potential atmospheric composition raise questions about its ability to support life as we know it. Some scientists argue that the pressure at the planet's surface might be too high for life, while others suggest that conditions could be suitable in certain atmospheric layers. The detection of water vapor in K218b's atmosphere has also fueled discussions. While this discovery excited many researchers, others caution against overinterpretation, pointing out that the presence of water vapor alone does not guarantee habitable conditions. The debate continues over how much can be inferred about the planet's overall composition and potential for hosting life based on these atmospheric observations. Scientists often encounter conflicting data or interpretations when studying exoplanets like K218b, and they employ various methods to reconcile these discrepancies. For K218b, researchers have used multiple observation techniques, including transit spectroscopy and radial velocity measurements, to gather data about its size, mass, and atmospheric composition. When conflicting information arises, scientists carefully review their methodologies and data analysis processes. They may re-examine their assumptions, recalibrate their instruments, or conduct additional observations to verify their findings. In some cases, they might develop new models or algorithms to better interpret the available data. Collaboration plays a crucial role in resolving conflicts. Scientists from different institutions and backgrounds often work together, sharing their expertise and cross-checking each other's results. This peer review process helps identify potential errors or biases in individual studies and leads to more robust conclusions. For K218b specifically, ongoing debates about its nature as a mini-Neptune or super-Earth highlight the importance of continued observation and analysis. As our understanding of exoplanets evolves and technology improves, scientists remain open to revising their interpretations based on new evidence, ensuring that our knowledge of K218b and similar worlds continues to grow and refine over time. Scientists employ a rigorous and collaborative approach to reach consensus on findings related to exoplanets like K218b. This process begins with data collection from various sources, including space telescopes such as Kepler, Hubble, and James Webb. These instruments provide crucial information about the planet's size, orbit, and atmospheric composition. Once data is gathered, researchers analyze it using sophisticated computer models and statistical techniques. They cross-reference their findings with existing knowledge about planetary formation and evolution. This analysis often involves teams from different institutions working independently on the same dataset to ensure reproducibility of results. Peer review plays a vital role in the consensus-building process. Scientists submit their findings to respected journals, where experts in the field scrutinize the methods, data, and conclusions. This critical evaluation helps identify potential errors or alternative interpretations. The scientific community then discusses and debates these findings at conferences and through further publications. Consensus emerges gradually as multiple studies converge on similar conclusions. For K218b, this process has led to agreement on its status as a potentially habitable super-Earth with a hydrogen-rich atmosphere. However, scientists remain cautious and open to new data that might challenge or refine our understanding of this intriguing exoplanet. The discovery of K218b has garnered significant attention in the media, often being portrayed as a potential Earth-like world. Many news outlets have emphasized its location within the habitable zone of its star, a region where conditions might allow for liquid water on the surface. This has led to headlines suggesting K218b could be a candidate for hosting life. Media reports have frequently highlighted the detection of water vapor in the planet's atmosphere, a finding that has fueled public imagination about the possibility of an ocean world. However, some coverage has been more measured, noting that K218b is much larger than Earth and likely has a dense hydrogen atmosphere, making it more similar to Neptune than our home planet. Scientists have been quoted in various articles, urging caution in interpreting these findings. They stress that while the presence of water vapor is exciting, it does not necessarily indicate conditions suitable for life as we know it. The intense radiation from the planet's red dwarf star and its potentially crushing atmospheric pressure are factors that complicate the habitability question. Overall, the media portrayal of K218b reflects a balance between scientific excitement and the need for further research. It serves as a reminder of the ongoing quest to find potentially habitable worlds beyond our solar system. while also highlighting the complexities involved in characterizing distant exoplanets. The discovery of K218b has significantly boosted public interest in exoplanet research, capturing the imagination of both scientists and the general public. This distant world, located about 124 light-years from Earth, gained attention for its potential to harbor conditions suitable for life as we know it. K218b orbits within the habitable zone of its parent star, a region where temperatures could allow for the existence of liquid water on a planet's surface. This characteristic alone piqued curiosity, but the real excitement came when researchers detected water vapor in its atmosphere. This marked the first time water vapor was found in the atmosphere of an exoplanet within the habitable zone. The findings sparked widespread media coverage and public discussions about the possibility of life beyond our solar system. It brought the concept of habitable exoplanets from the realm of science fiction into scientific reality, making the search for extraterrestrial life seem more tangible and immediate to many people. K218b has also highlighted the rapid advancements in exoplanet detection and analysis techniques. It demonstrated how far our capabilities have come in studying distant worlds, further fueling enthusiasm for future exoplanet missions and research projects. This increased public interest has, in turn, helped garner support for continued funding and exploration in this field, potentially accelerating our quest to find life elsewhere in the universe. The scientific information about K218b has been reported with increasing accuracy as our observational capabilities have improved. Initially discovered in 2015 by the Kepler Space Telescope, this exoplanet has since been the subject of intense study using various instruments, including the Hubble Space Telescope and ground-based observatories. Early reports correctly identified K218b as a super-Earth, a planet larger than Earth but smaller than Neptune. However, the initial estimates of its size and mass have been refined over time. Current data suggests the planet is about 2.5 times the diameter of Earth and about 8 times its mass. One of the most significant developments in our understanding of K218b came in 2019, when researchers using the Hubble Space Telescope detected water vapor in its atmosphere. This finding was widely reported and largely accurate, though some media outlets may have overstated the implications for the planet's habitability. More recent studies have provided additional insights into the planet's composition and potential structure. Scientists now believe K18b likely has a large hydrogen and helium atmosphere surrounding a rocky or icy core. While these findings are based on the best available data and models, they are subject to further refinement as new observations are made and analysis techniques improve. K218b has garnered significant attention in recent years, but several misconceptions have taken root in public discourse. One common misunderstanding is that K218b is definitively Earth-like or habitable. While this exoplanet does reside in its star's habitable zone and has a potentially suitable temperature range, its actual conditions remain largely unknown. Another misconception is that the detection of water vapor in its atmosphere guarantees the presence of liquid water on its surface. In reality, the planet's size and mass suggest it might be a mini Neptune rather than a rocky world, potentially lacking a solid surface altogether. The water vapor detected could be part of a thick, gaseous envelope rather than indicative of surface oceans. Many also assume that K218b's position in the habitable zone automatically makes it hospitable to life as we know it. However, the planet receives significantly more radiation from its star than Earth does from the Sun, and its larger size suggests it might have a much stronger gravitational pull. These factors could create conditions vastly different from those on Earth, potentially challenging for life to emerge or thrive. Lastly, there's a tendency to overlook the considerable distance between Earth and K218b. At about 124 light-years away, detailed study and potential exploration of this exoplanet remain significant challenges, despite the excitement its discovery has generated in the scientific community and beyond. Scientists employ various methods to convey complex information about exoplanets like K218b to the general public. They often start by emphasizing the most relatable and exciting aspects of their discoveries. For K218b, this might include highlighting its potential habitability and the presence of water vapor in its atmosphere. To make the information more digestible, researchers frequently use analogies and comparisons to objects or concepts familiar to everyday people. They might describe K218b in terms of its size relative to Earth, or compare its orbit to planets in our solar system. Visual aids such as artist impressions and infographics also play a crucial role in helping the public grasp abstract concepts and visualize distant worlds. Media partnerships are another key strategy. Scientists collaborate with journalists and science communicators to translate their findings into accessible language for news articles, documentaries, and social media content. These partnerships help bridge the gap between technical jargon and public understanding. Lastly, many research institutions and space agencies host public engagement events, webinars, and interactive online platforms. These initiatives allow scientists to directly interact with the public, answering questions and providing context for their discoveries about K218b and other exoplanets. By combining these approaches, researchers aim to spark curiosity and foster a broader appreciation for exoplanet science. Social media has been instrumental in disseminating information about K218b to a wide audience. Platforms like Twitter, Facebook, and Instagram have allowed scientists and space agencies to share updates and discoveries about this intriguing exoplanet in real time. These posts often include eye-catching images, infographics, and simplified explanations of complex scientific concepts, making the information more accessible to the general public. Hashtags related to K218b have trended on various platforms, sparking discussions and encouraging users to share and engage with the content. This viral spread of information has helped generate excitement and interest in exoplanet research among people who might not typically follow scientific news. Space enthusiasts and science communicators have also played a crucial role in amplifying the reach of K218b news. They often break down complex scientific papers into more digestible content, creating videos, podcasts, and blog posts that explain the significance of discoveries related to this exoplanet. This user-generated content helps to further spread awareness and understanding of K218b beyond traditional media outlets. The rapid and widespread sharing of information about K218b on social media has also contributed to increased public support for space exploration and exoplanet research. By making these scientific discoveries feel more immediate and relevant, social media has helped foster a sense of connection between the public and the ongoing search for potentially habitable worlds beyond our solar system. K218b has not gained significant representation in popular culture compared to other exoplanets. This super-Earth, discovered in 2015, orbits a red dwarf star about 124 light-years from Earth. While it has captured the attention of astronomers and exoplanet enthusiasts, its presence in mainstream media and entertainment has been limited. The planet gained some public interest in 2019 when researchers announced the detection of water vapor in its atmosphere. This discovery sparked discussions about the potential habitability of exoplanets and the search for life beyond our solar system. News outlets and science programs covered the finding, bringing K218b into the spotlight briefly. Despite this attention, K218b has not yet become a prominent fixture in science fiction literature, movies, or television shows. Unlike some other exoplanets, it has not inspired specific storylines or served as a setting for fictional narratives. This could be due to its relatively recent discovery and the evolving nature of our understanding of its characteristics. As our knowledge of K218b and similar exoplanets grows, it is possible that they may feature more prominently in future science fiction and popular science discussions. The potential for these distant worlds to capture the public imagination remains, especially as we continue to search for planets that could potentially harbor life. The discovery of K218b has sparked numerous educational initiatives aimed at fostering interest in exoplanet research and astrobiology. Universities and research institutions have developed new courses and programs focusing on the study of potentially habitable worlds beyond our solar system. These programs often use K218b as a case study to illustrate the methods of exoplanet detection and characterization. Science museums and planetariums have created interactive exhibits that allow visitors to explore virtual models of K218b, helping the public understand the nature of this intriguing world. Some of these exhibits incorporate augmented reality technology, enabling visitors to visualize the planet's atmosphere and potential surface conditions. Citizen science projects have also emerged, inviting amateur astronomers and enthusiasts to participate in the search for similar exoplanets. These initiatives often use data from space telescopes, teaching participants about data analysis and the scientific method while contributing to real research. Educational outreach programs have been developed for schools, using K218b as a launching point to discuss broader topics in astronomy, planetary science, and the search for life beyond Earth. These programs often include hands-on activities and experiments that simulate the techniques used to study distant worlds, inspiring the next generation of space scientists and explorers. Public fascination with K218b often centers on its potential to harbor life, but scientists approach this exoplanet with more measured enthusiasm. While many people imagine K218b as a water world teeming with alien fish, researchers understand that its conditions are far more complex and potentially inhospitable. The public tends to focus on the presence of water vapor in K218b's atmosphere, seeing this as a clear sign of habitability. However, scientists know that water vapor alone does not guarantee liquid water on the surface or conditions suitable for life as we know it. The planet's size and mass suggest it could be a mini Neptune rather than a rocky world, with a thick hydrogen atmosphere that would create intense pressure at lower levels. Temperature is another area where public perception and scientific understanding diverge. Many assume that because K218b orbits in its star's habitable zone, it must have Earth-like temperatures. Scientists, however, consider a broader range of factors, including atmospheric composition and the properties of its host star, which affect the planet's actual surface conditions. Researchers also emphasize the limitations of current data on K218b, recognizing that much remains unknown about its true nature. While the public may see definitive answers, scientists see K218b as an intriguing subject for further study, representing an important step in our quest to understand the diversity of worlds beyond our solar system. Scientists studying K218b have a crucial responsibility to manage public expectations carefully and accurately. As exciting as the discovery of this potentially habitable exoplanet is, researchers must strike a balance between sharing their findings and avoiding sensationalism. One key aspect of this responsibility is clearly communicating the limitations of our current knowledge. While K218b shows promising signs, such as its location in the habitable zone and the potential presence of water vapor in its atmosphere, scientists must emphasize that these factors alone do not guarantee habitability or the presence of life. Researchers should also educate the public about the vast distances involved and the current technological limitations that prevent us from directly observing or visiting K218b. By providing context about the challenges of exoplanet research, scientists can help temper unrealistic expectations while still conveying the significance of their discoveries. Ultimately, scientists must strive for transparency and accuracy in their communications, fostering public interest and understanding of exoplanet research without overpromising or speculating beyond the available evidence. This approach ensures that the public remains engaged and informed about the ongoing search for potentially habitable worlds beyond our solar system. The discovery of potentially habitable exoplanets like K218b raises profound ethical questions for humanity. As we peer into distant solar systems, we must grapple with the implications of finding worlds that could harbor life. One key consideration is how we should approach the study of these planets. Should we limit ourselves to remote observations, or should we actively seek ways to explore them? The risk of contaminating a pristine alien biosphere with Earth microbes is a serious concern. Any future missions to these worlds would need to follow strict planetary protection protocols to avoid disrupting potential ecosystems. Another ethical dimension involves the potential for colonization. If we find a habitable world, do we have the right to settle it? This question becomes even more complex if we detect signs of existing life. We must carefully weigh our own species' needs against the preservation of alien life forms and environments. There are also broader philosophical implications to consider. The discovery of life beyond Earth would profoundly impact our understanding of our place in the universe. It could challenge religious and cultural beliefs, potentially causing societal upheaval. As scientists, we have a responsibility to consider how we communicate such findings to the public and prepare society for their ramifications. The discovery of life on K218b would be a watershed moment in human history, fundamentally altering our understanding of our place in the universe. This exoplanet, located about 124 light-years from Earth, has captured scientific interest due to its potential habitability. If life were confirmed on K218b, it would provide concrete evidence that we are not alone in the universe. This revelation could spark a paradigm shift in various fields, from science and philosophy to religion and culture. Scientific research would likely see a surge in funding and interest, particularly in areas related to astrobiology, space exploration, and the search for extraterrestrial intelligence. The nature of the life discovered would greatly influence its impact. Simple microbial life would be groundbreaking, but the detection of complex or intelligent life forms would be truly revolutionary. It could prompt us to re-evaluate our cosmic significance and potentially lead to attempts at communication or even long-term plans for interstellar travel. Socially, such a discovery might unite humanity with a shared sense of cosmic citizenship, potentially diminishing the importance of national and cultural differences on Earth. However, it could also raise new concerns about potential threats from beyond our planet, influencing global politics and defense strategies. The implications would be far-reaching, touching nearly every aspect of human society and potentially reshaping our collective future. The potential colonization of K218b raises profound ethical questions that humanity must grapple with as we look to the stars. This exoplanet, located about 124 light-years from Earth, has captured the imagination of scientists and the public alike due to its potential habitability. One of the primary ethical concerns is the impact human colonization might have on any existing life forms on K218b. If microbial or even more complex life exists there, our presence could disrupt or destroy entire ecosystems that have evolved over billions of years. We must consider whether we have the right to potentially eradicate alien life forms for our own benefit. Another crucial consideration is the long-term sustainability of such a colonization effort. The immense resources required to transport humans across vast interstellar distances and establish a self-sustaining colony raise questions about the justification for such an endeavor. Would these resources be better spent addressing pressing issues on Earth, such as climate change or global inequality? The selection process for potential colonists also presents ethical challenges. Who gets to go? How do we ensure fairness and diversity in the selection process? There are also concerns about the physical and psychological well-being of colonists who would be isolated from Earth, potentially for generations. The ethical implications of creating a new branch of humanity, separated by time and space from its origin, are profound and far-reaching. Scientists studying K218b face a delicate balance between advancing our understanding of potentially habitable exoplanets and communicating their findings responsibly to the public. They must carefully analyze data from telescopes and space missions, interpreting subtle clues about the planet's atmosphere and potential conditions. At the same time, they need to convey their discoveries in a way that sparks interest without overstating the implications. When discussing K218b, researchers emphasize the uncertainties in their findings. They explain that while the planet orbits in its star's habitable zone and shows signs of water vapor in its atmosphere, this does not guarantee the presence of liquid water or life. Scientists stress that our current technology limits our ability to definitively characterize distant worlds. To maintain scientific integrity, experts often use precise language when describing K218b, avoiding sensationalism that could lead to misinterpretation. They contextualize their findings within the broader search for potentially habitable worlds, highlighting how each discovery contributes to our evolving understanding of planetary systems. Ultimately, scientists aim to foster public engagement with exoplanet research while maintaining rigorous standards of evidence. They strive to convey the excitement of exploration and discovery without making unfounded claims, ensuring that our collective journey to understand the cosmos remains grounded in robust scientific methodology. The search for extraterrestrial life is guided by a set of ethical principles designed to protect both potential alien life forms and our own planet. These guidelines, often referred to as planetary protection protocols, are overseen by international organizations such as the Committee on Space Research. One of the primary ethical considerations is the prevention of biological contamination. When sending probes or spacecraft to other celestial bodies, scientists take great care to sterilize equipment to avoid introducing Earth microbes to potentially habitable environments. This precaution serves two purposes. It prevents the accidental seeding of life on other worlds and ensures that any life detected is truly native to that environment. Ethical guidelines also address how we should respond if we do discover extraterrestrial life. Scientists are encouraged to prioritize observation and non-interference, especially when dealing with potential intelligent life. This approach aims to minimize our impact on alien ecosystems and cultures, respecting their right to develop without human intervention. There are also ongoing discussions about the ethics of broadcasting messages into space. Some argue that actively seeking contact with alien civilizations could pose risks to humanity, while others believe it is our duty to reach out. These debates highlight the complex ethical landscape surrounding our search for life beyond Earth, balancing scientific curiosity with caution and responsibility. The discovery of K218b has sparked new conversations about space preservation and our approach to exploring potentially habitable worlds. This exoplanet, located about 124 light-years from Earth, orbits within the habitable zone of its star and possesses an atmosphere that could potentially support life. As we continue to identify more planets like K218b, the scientific community is increasingly focused on developing protocols for studying these worlds without contaminating them. The concept of planetary protection becomes even more critical when we consider the possibility of microbial life existing on these distant bodies. Scientists must balance the desire for exploration with the need to preserve these environments in their natural state. The discovery also raises questions about the long-term preservation of space itself. As we look toward future interstellar missions, there is growing concern about the impact of human activity on the cosmic environment. This includes issues such as space debris, light pollution from satellites, and the potential for resource exploitation on other worlds. K218b and similar exoplanets are now seen as valuable scientific resources that require careful stewardship. This shift in perspective is influencing discussions about international space law and the need for global cooperation in space exploration. The ultimate goal is to ensure that our quest for knowledge does not come at the cost of irreversibly altering or damaging these distant, potentially life-bearing worlds. Sending messages or probes to K218b, an exoplanet approximately 124 light-years from Earth, presents several potential risks that scientists must carefully consider. One significant concern is the possibility of contamination. Any probe or message we send could potentially introduce Earth-based microorganisms or materials to the exoplanet's environment. This could have unforeseen consequences for any potential life forms that might exist on K218b, potentially disrupting or even destroying delicate ecosystems before we have a chance to study them. Another risk lies in the realm of interstellar communication. By sending messages to K218b, we would be announcing our presence to any potential intelligent life in that star system. Some scientists argue that this could be dangerous, as we have no way of knowing the intentions or technological capabilities of any extraterrestrial civilizations that might receive our signals. This concern, often referred to as the dark forest theory, suggests that it might be safer to remain undetected in the vastness of space. There are also technical challenges and risks to consider. The immense distance to K218b means that any probes we send would take an extremely long time to arrive, potentially outlasting the technology and scientific objectives that prompted their launch. Additionally, the harsh conditions of interstellar space could damage or destroy probes before they reach their destination, resulting in wasted resources and missed opportunities for scientific discovery. The discovery of K218b has sparked diverse reactions across cultures and belief systems worldwide. For many, This potentially habitable exoplanet represents a profound shift in our understanding of life in the universe. In Western scientific communities, K218b is seen as a promising candidate for further study, with its potential water vapor atmosphere and location in the habitable zone of its star fueling excitement about the possibility of extraterrestrial life. Some religious groups view K218b's discovery as a testament to the vastness and complexity of creation, interpreting it as further evidence of divine design. Others see it as a challenge to traditional beliefs about humanity's unique place in the cosmos. Indigenous cultures with strong connections to celestial bodies often incorporate such discoveries into their existing cosmologies, viewing K218b as an extension of their understanding of the interconnectedness of all things. Philosophers and ethicists are grappling with the implications of potentially habitable worlds, questioning how the discovery of extraterrestrial life might impact our moral frameworks and sense of cosmic significance. Some argue that finding life elsewhere would unite humanity under a shared sense of cosmic citizenship, while others worry it could diminish our sense of uniqueness and purpose. Across the board, K218b has ignited imaginations and sparked conversations about our place in the universe. As we continue to explore and learn more about this distant world, its impact on our collective worldview is likely to evolve, challenging and expanding our understanding of life, existence, and our role in the cosmic tapestry. Public opinion should certainly be considered in decisions about further research on K218b, but it should not be the sole or primary factor guiding scientific exploration. The scientific community and space agencies must carefully balance public interest and support with the rigorous pursuit of knowledge and the potential scientific value of continued study. K218b has captured public imagination as a potentially habitable exoplanet, which can help generate enthusiasm and support for space exploration. This public interest can be valuable in securing funding and resources for further research. However, scientists must also prioritize research based on scientific merit and the potential for advancing our understanding of exoplanets and the possibility of life beyond Earth. Ultimately, decisions about researching K218b should be made by experts in the field, taking into account the scientific questions that can be answered, the technological capabilities available, and the broader goals of exoplanet research. Public engagement and education about the significance of such research are crucial, but the direction of scientific inquiry should be guided primarily by scientific considerations rather than popular opinion. It is important to strike a balance between addressing public curiosity and maintaining scientific integrity. By fostering open communication between scientists and the public, we can ensure that research on K218b and other exoplanets continues to advance our knowledge while also capturing the imagination of people around the world. The study of K218b, an exoplanet about twice the size of Earth, could significantly influence our approach to environmental stewardship on our own world. This distant planet, located 124 light-years away, has captured the attention of scientists due to its potential habitability and the presence of water vapor in its atmosphere. As we delve deeper into understanding K218b, we gain valuable insights into the delicate balance required for a planet to sustain life. This knowledge underscores the importance of maintaining Earth's own fragile ecosystems. The discovery of water on K218b reminds us of the crucial role this molecule plays in supporting life, prompting us to reevaluate our management of Earth's water resources. Furthermore, studying the atmosphere of K218b provides a unique perspective on climate dynamics. By comparing its atmospheric composition to Earth's, we can better understand the impact of greenhouse gases and other factors on planetary climates. This comparative analysis could inform our strategies for addressing climate change and improving air quality on our home planet. The exploration of K218b also highlights the rarity of habitable worlds in the universe. This realization may foster a greater appreciation for Earth's unique conditions, encouraging more sustainable practices and conservation efforts. As we continue to search for life beyond our solar system, the lessons learned from K218b serve as a powerful reminder of our responsibility to protect and preserve the extraordinary planet we call home. Exoplanet research has undergone a remarkable transformation since the first confirmed discovery in 1995. Initially, astronomers could only detect massive planets orbiting close to their stars using the radial velocity method. This technique measures the slight wobble of a star caused by the gravitational pull of an orbiting planet. As technology advanced, new methods emerged. The transit method, which detects the dimming of starlight as a planet passes in front of its star, became a powerful tool. This approach not only allowed for the discovery of smaller planets, but also provided information about their size and atmospheric composition. The launch of space-based telescopes like Kepler and TESS revolutionized the field. These missions have discovered thousands of exoplanets, revealing a diverse array of planetary systems. We now know that planets are common throughout the galaxy, with many stars hosting multiple worlds. Recent advancements in direct imaging and spectroscopy have allowed astronomers to study exoplanet atmospheres in unprecedented detail. This has opened up new avenues for the search for potentially habitable worlds and even signs of life beyond our solar system. The evolution of exoplanet research has transformed our understanding of planetary formation and the potential for life in the universe. The search for exoplanets has been a fascinating journey of scientific discovery. The first confirmed detection of an exoplanet orbiting a main sequence star came in 1995, when Michel Mayor and Didier Queloz discovered 51 Pegasi b. This hot Jupiter orbiting a sun-like star revolutionized our understanding of planetary systems and kicked off the era of exoplanet astronomy. A significant milestone occurred in 2009 with the launch of the Kepler Space Telescope. Kepler used the transit method to detect thousands of exoplanet candidates, vastly expanding our catalogue of known worlds beyond our solar system. This mission revealed that planets are common in our galaxy, with some estimates suggesting there could be billions of potentially habitable worlds in the Milky Way alone. The next major breakthrough came in 2015 with the discovery of Proxima Centauri b, an Earth-sized planet orbiting in the habitable zone of our nearest stellar neighbor. This finding excited scientists and the public alike, as it brought the possibility of potentially habitable worlds tantalizingly close to our cosmic doorstep. In 2017, the TRAPPIST-1 system was announced, featuring 7 Earth-sized planets orbiting a small, cool star. This system captured imaginations worldwide and demonstrated the diversity of planetary systems in our galaxy. These discoveries set the stage for the exploration of more potentially habitable worlds, leading to the investigation of K2-18b and other intriguing exoplanets. Exoplanet research has undergone a remarkable evolution since the first confirmed discovery in 1995. Initially, astronomers were simply thrilled to find any planets beyond our solar system, regardless of their characteristics. The focus was on detection, using methods like radial velocity measurements to spot the gravitational wobble of stars caused by orbiting planets. As detection techniques improved, the emphasis shifted towards finding potentially habitable worlds. Scientists began searching for planets in the Goldilocks zone, where conditions might allow for liquid water on the surface. This period saw increased interest in Earth-sized planets and super-Earths, which could potentially support life as we know it. More recently, exoplanet research has broadened its scope significantly. Scientists are now studying the atmospheres of these distant worlds, looking for biosignatures that could indicate the presence of life. Advanced telescopes and spectroscopic techniques allow researchers to analyze the chemical composition of exoplanet atmospheres, searching for gases like oxygen or methane that might suggest biological activity. Furthermore, the field has expanded to include the study of exoplanet formation and evolution. Researchers are investigating how planetary systems develop and change over time, providing crucial insights into the history and future of our own solar system. This holistic approach to exoplanet science is painting a more complete picture of the diverse and fascinating worlds that populate our galaxy. K2-18b, an exoplanet discovered in recent years, has sparked considerable interest in the astronomical community. This distant world challenges some long-held assumptions about potentially habitable planets, while supporting other theories that have gained traction in recent decades. Traditionally, scientists focused their search for habitable worlds on planets similar to Earth in size and composition, orbiting stars like our Sun at distances allowing for liquid water on the surface. K218b, however, is what we call a super-Earth or mini-Neptune, significantly larger and more massive than our home planet. Its discovery supports the growing theory that habitability might extend to a broader range of planetary types than previously thought. The presence of water vapor in K218b's atmosphere, detected through advanced spectroscopic techniques, lends support to the idea that planets orbiting red dwarf stars could potentially harbor life. This challenges historical skepticism about the habitability of worlds around these cooler, more common stars, which were once thought too volatile or radiation-prone to host life-bearing planets. Furthermore, K218b's existence in the habitable zone of its star, despite its size, challenges older models of planetary formation and evolution. It suggests that gas-rich planets might retain their atmospheres even when orbiting close to their stars, expanding our understanding of where we might find potentially life-supporting worlds in the cosmos. K218b represents a significant milestone in our ongoing quest to find habitable worlds beyond our solar system. This exoplanet, located approximately 124 light-years from Earth, orbits a red dwarf star in the constellation Leo. Its discovery and subsequent analysis have expanded our understanding of potentially life-supporting environments in the cosmos. What makes K218b particularly intriguing is its position within the habitable zone of its star, often called the Goldilocks zone, where conditions could allow for liquid water to exist on the surface. This alone would be noteworthy, but recent observations have revealed even more exciting possibilities. Scientists have detected water vapor in the atmosphere of K218b, marking the first time such a discovery has been made for a planet in the habitable zone. The presence of water vapor, combined with the planet's size and location, suggests that K218b could be a super-Earth or a mini-Neptune. This classification places it in a category of planets not found in our solar system, broadening our perspective on the diverse forms exoplanets can take. The potential for liquid water and an atmosphere on K218b opens up tantalizing possibilities for the existence of microbial life. While K218b itself may not be a perfect Earth analog due to its size and the nature of its host star, its discovery and continued study contribute valuable data to our search for extraterrestrial life. It helps refine our understanding of what constitutes a habitable world and guides future exoplanet research, bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe? The study of K218b benefited greatly from the wealth of knowledge accumulated through previous exoplanet discoveries. Scientists applied refined detection and analysis techniques honed over years of exoplanet research. One key lesson was the importance of multiple observation methods. Researchers used both the transit method, which detects planets as they pass in front of their star, and the radial velocity method, which measures the star's wobble due to the planet's gravitational pull. This combined approach provided more accurate data on K218b's size and mass. Another crucial insight from past discoveries was the significance of atmospheric analysis. Earlier studies of hot Jupiters and super-Earths demonstrated that a planet's atmosphere could reveal much about its composition and potential habitability. In the case of K218b, scientists used advanced spectroscopic techniques to analyze the starlight filtered through its atmosphere, allowing them to detect water vapor. The exploration of K218b also reflected lessons learned about the diversity of exoplanets. Previous discoveries showed that planets could exist in unexpected places and forms, expanding our understanding of planetary formation and evolution. This knowledge encouraged researchers to look beyond traditional habitable zone definitions and consider a broader range of potentially life-supporting environments. Lastly, past exoplanet studies emphasized the need for patience and repeated observations. The confirmation of K218b and the detection of water in its atmosphere required multiple observations over several years, demonstrating the long-term commitment necessary for robust exoplanet research. The concept of the habitable zone has undergone significant changes since its introduction. Initially, scientists defined it as the region around a star where liquid water could exist on a planet's surface. This narrow definition focused primarily on temperature, considering a planet's distance from its star as the key factor. As our understanding of planetary systems grew, the definition expanded. Scientists began to consider factors beyond just temperature, such as a planet's atmosphere, magnetic field, and geological activity. These elements play crucial roles in maintaining conditions suitable for life as we know it. The habitable zone now encompasses a broader range of possibilities, including worlds with subsurface oceans or alternative biochemistries. K218b, a planet discovered in 2015, exemplifies this evolving concept. Located about 124 light-years from Earth, this super-Earth orbits a red dwarf star. Initially, K218b's position within its star's traditional habitable zone sparked excitement. However, its classification as potentially habitable became more complex upon closer examination. Recent studies have detected water vapor and possibly methane in K218b's atmosphere, fueling speculation about its potential to harbor life. Yet its size and mass suggest it might be more like Neptune than Earth, with a thick hydrogen atmosphere unsuitable for life as we know it. K218b thus challenges our understanding of habitability, prompting scientists to reconsider what conditions might support life beyond our solar system and expanding our search for potentially habitable worlds. Astronomers from various eras would have been fascinated by K218b, a planet that challenges our understanding of habitability beyond Earth. Johannes Kepler, the 17th-century astronomer who discovered the laws of planetary motion, would have been intrigued by this distant world. Kepler was one of the first to seriously consider the possibility of life on other planets, and K218b's potential for liquid water would have captured his imagination. Carl Sagan, the renowned 20th-century astronomer and science communicator, would have been especially excited about K218b. Sagan was a pioneer in the search for extraterrestrial life and played a crucial role in designing messages for potential alien civilizations. The discovery of water vapor in the atmosphere of K218b would have aligned perfectly with his vision of cosmic exploration and the potential for life beyond Earth. Frank Drake, the astronomer who formulated the Drake equation to estimate the number of civilizations in our galaxy, would have seen K218b as a valuable data point. This planet's characteristics would have informed his calculations about the prevalence of potentially habitable worlds. Similarly, Jill Tarter, a key figure in the search for extraterrestrial intelligence, would have viewed K218b as a prime target for further investigation in the quest to find signs of life in the universe. The discovery of K218b marks a significant milestone in our quest to find potentially habitable worlds beyond our solar system. This super-Earth, located about 124 light-years away, orbits within the habitable zone of its red dwarf star. What sets K218b apart is the detection of water vapor in its atmosphere, a crucial ingredient for life as we know it. Throughout history, astronomical discoveries have reshaped our understanding of the universe. Galileo's observations of Jupiter's moons in the 17th century challenged the geocentric model, while the discovery of exoplanets in the late 20th century opened up a new frontier in the search for alien worlds. The confirmation of gravitational waves in 2015 provided a new way to observe the cosmos. K218b stands out because it combines several key factors. It is potentially habitable, has an atmosphere we can study, and is close enough for detailed observation. This makes it an ideal candidate for future research into the potential for life beyond Earth. While not as paradigm-shifting as some historical discoveries, K218b represents a crucial step in our ability to characterize distant worlds. The significance of K218b lies not just in its individual properties, but in what it represents for the future of exoplanet research. It demonstrates that we now have the technology to detect atmospheres and potential biosignatures on distant planets, bringing us closer to answering one of humanity's most profound questions: are we alone in the universe? The history of exoplanet research provides valuable insights into our potential future exploration of K218b. When astronomers first began searching for planets beyond our solar system, they focused on detecting massive gas giants orbiting close to their stars. These hot Jupiters were easier to find due to their size and strong gravitational effects on their host stars. As detection methods improved, we gradually discovered smaller, rocky planets and those in the habitable zones of their stars. K218b represents the next frontier in exoplanet research. It is a super-Earth, larger than our planet but smaller than Neptune, orbiting in the habitable zone of its star. The discovery of water vapor in its atmosphere marked a significant milestone, as it was the first time we detected water on a potentially habitable exoplanet. This finding echoes the progression of exoplanet research, where each new discovery pushes the boundaries of our knowledge and capabilities. Looking ahead, the study of K218b will likely follow a similar pattern to previous exoplanet research. We can expect increasingly detailed observations of its atmosphere, searching for additional chemical signatures that might indicate the presence of life. Future telescopes and instruments will allow us to create more accurate models of its climate and potential surface conditions. Just as the history of exoplanet research has been marked by surprising discoveries that challenged our assumptions, the study of K218b may reveal unexpected characteristics that reshape our understanding of planetary formation and the potential for life beyond Earth. This continuous cycle of observation, analysis, and revelation will drive our exploration of K218b and other intriguing exoplanets in the coming years. Research on K218b has been a truly international effort, involving scientists and institutions from numerous countries around the world. The United Kingdom has played a significant role, with researchers from University College London making key discoveries about the exoplanet's atmosphere. Canada has also been at the forefront, with scientists from the University of Montreal contributing to important studies on K218b's potential habitability. The United States has been heavily involved, with NASA's Hubble Space Telescope providing crucial data for analyzing the planet's atmosphere. Additionally, researchers from American institutions such as the Massachusetts Institute of Technology have been instrumental in advancing our understanding of this intriguing world. European countries have also made substantial contributions. German scientists from the Max Planck Institute for Astronomy have been involved in studying K218b's characteristics. French researchers from institutions like the Paris Observatory have participated in analyzing data and developing models to better understand the planet's nature. The collaborative nature of this research extends to other nations as well, with contributions from scientists in countries such as Japan, Italy, and Spain. This global effort highlights the international cooperation that often characterizes cutting-edge exoplanet research, as scientists worldwide work together to unravel the mysteries of distant worlds like K218b. Scientists from various countries work together to unravel the mysteries of K218b, an exoplanet that has captured the attention of astronomers worldwide. Research institutions in the United States, United Kingdom, and Canada have joined forces to analyze data from space telescopes and ground-based observatories. These international collaborations allow for the sharing of resources, expertise, and observing time on powerful instruments. Teams coordinate their efforts to study K218b from multiple angles, examining its atmosphere, orbit, and potential habitability. By combining data from different sources, scientists can cross-verify their findings and build a more comprehensive understanding of this distant world. Regular video conferences and data-sharing platforms enable researchers to discuss their latest discoveries and plan future observations. This global approach to exoplanet research accelerates scientific progress and fosters innovation in detection and analysis techniques. As new information about K218b emerges, these international partnerships ensure that the scientific community can quickly validate and build upon each breakthrough. The study of K218b serves as a prime example of how modern astronomy transcends national boundaries, uniting scientists in the common goal of expanding our knowledge of the universe and the potential for life beyond Earth. Space agencies like the National Aeronautics and Space Administration and the European Space Agency play crucial roles in advancing our understanding of exoplanets like K218b. These organizations develop, launch, and operate sophisticated space telescopes and instruments that are essential for detecting and studying distant worlds. The Kepler Space Telescope, a NASA mission, initially discovered K218b in 2015 during its extended K2 mission. This discovery laid the foundation for further investigations of this intriguing exoplanet. Following this, the Hubble Space Telescope, a joint project between NASA and ESA, was used to analyze the atmosphere of K2-18b, revealing the presence of water vapor. These agencies also foster international collaboration, bringing together scientists and engineers from around the world to pool knowledge and resources. They provide funding for research projects, data analysis, and theoretical modeling, which are all crucial for interpreting the observations and understanding the nature of exoplanets like K2-18b. Furthermore, NASA and ESA are developing next-generation telescopes, such as the James Webb Space Telescope, which will enable even more detailed studies of exoplanet atmospheres. These future missions promise to greatly enhance our ability to characterize potentially habitable worlds beyond our solar system, including further investigations of K2-18b. International collaboration is crucial in the study of exoplanets like K2-18b. Researchers from various countries share data and resources through a network of observatories, space telescopes, and scientific institutions. The initial discovery of K2-18b was made using data from the Kepler Space Telescope, which was then made available to scientists worldwide. Subsequent observations have involved multiple facilities, including the Hubble Space Telescope and ground-based observatories in different countries. These observations generate massive amounts of data that are stored in international astronomical databases. Scientists can access these databases to analyze the information and contribute their findings to the global scientific community. Regular conferences, both virtual and in person, allow researchers to present their latest discoveries and discuss new theories about K2-18b. These gatherings foster collaboration and help coordinate future observation campaigns. Additionally, many research teams publish their findings in open-access journals, ensuring that their work is freely available to scientists and the public alike. This global approach to studying K2-18b not only accelerates scientific progress but also ensures that diverse perspectives and expertise are brought to bear on understanding this intriguing exoplanet. As new space telescopes and more powerful instruments come online, the international scientific community continues to refine its methods of data sharing and collaboration. Research on exoplanets like K2-18b often requires global cooperation, bringing together scientists and resources from various countries. This international collaboration, while crucial for advancing our understanding, does present several challenges. One significant hurdle is coordinating observations across different time zones and geographical locations. Telescopes and observatories worldwide need to work in sync to gather comprehensive data on K2-18b. This requires meticulous planning and communication to ensure all participants are aligned in their efforts. Data sharing and standardization pose another challenge. Different research institutions may use varying methods and equipment to study K2-18b, potentially leading to discrepancies in results. Establishing universal protocols for data collection, analysis, and interpretation becomes essential to ensure the reliability and comparability of findings across international teams. Funding disparities between nations can also impact collaborative efforts. Some countries may have more advanced technology or greater financial resources to dedicate to K2-18b research. Balancing contributions and ensuring equitable access to data and credit for discoveries can be delicate issues to navigate in international partnerships. The study of K2-18b, an exoplanet of great interest to astronomers, has become a truly international endeavor. Scientists from various countries bring their specialized knowledge and advanced technologies to unravel the mysteries of this distant world. Canadian researchers have been at the forefront of analyzing K2-18b's atmosphere, using sophisticated computer models to interpret data from space telescopes. Their expertise in atmospheric science has been crucial in determining the potential habitability of this super-Earth. Teams from the United Kingdom have contributed significantly to the development and use of high-precision spectrographs. These instruments allow for detailed analysis of the light passing through K2-18b's atmosphere, revealing its chemical composition. British scientists have also been instrumental in coordinating international observation campaigns. In the United States, NASA's Hubble Space Telescope has played a vital role in gathering data about K2-18b. American researchers excel in managing and interpreting this wealth of information, often collaborating with scientists worldwide to refine our understanding of the exoplanet's characteristics. Currently, there are no specific international agreements governing the exploration or potential use of K218b. This exoplanet, located about 124 light-years from Earth, falls under the broader scope of international space law and agreements related to the exploration of outer space. The primary framework for space exploration is the Outer Space Treaty, formerly known as the Treaty on Principles Governing the Activities of States in the Exploration and Use of Outer Space, including the Moon and other celestial bodies. This treaty, which entered into force in 1967, provides the basic foundation for international space law. It stipulates that the exploration and use of outer space should be carried out for the benefit of all humanity, and that no nation can claim sovereignty over celestial bodies. While the Outer Space Treaty does not explicitly mention exoplanets like K218b, its principles would likely apply to any future exploration or use of such distant worlds. The treaty promotes international cooperation in space exploration and prohibits the placement of weapons of mass destruction in orbit or on celestial bodies. As our technological capabilities advance and the possibility of exploring or utilizing exoplanets becomes more realistic, it is likely that new international agreements or amendments to existing treaties will be necessary to address the unique challenges and opportunities presented by these distant worlds. Studying exoplanets like K218b brings scientists from around the world together in a shared pursuit of knowledge. This celestial body, located about 124 light-years away from Earth, has captured the attention of researchers globally due to its potential habitability. International collaboration is at the heart of exoplanet research. Observatories and space agencies from different countries contribute their unique capabilities and expertise to the study of K218b. For instance, the initial discovery of this exoplanet was made using data from the Kepler Space Telescope, a NASA mission. Follow-up observations have involved telescopes and instruments from various nations, fostering a spirit of cooperation. The study of K218b also promotes the exchange of ideas and methodologies among scientists from diverse backgrounds. Atmospheric modeling, data analysis techniques, and theoretical frameworks are shared and refined through international conferences, joint publications, and collaborative research projects. This cross-pollination of knowledge not only advances our understanding of K218b, but also strengthens scientific ties between nations. Moreover, the potential implications of studying K218b extend beyond pure science. The search for potentially habitable worlds resonates with people across cultures, serving as a unifying theme that transcends national boundaries. By working together on such compelling targets, scientists demonstrate the power of international cooperation in addressing fundamental questions about our place in the universe. Developing nations are increasingly contributing to exoplanet research, including studies of planets like K218b. These countries are leveraging their growing technological capabilities and scientific expertise to participate in this exciting field of astronomy. Many developing nations are investing in small to medium-sized telescopes and training their scientists in data analysis techniques. This allows them to contribute valuable observational data to global exoplanet surveys. Some countries are also developing their own space programs, with plans to launch satellites capable of exoplanet detection. Collaborative international projects are key in this area. Developing nations often partner with more established space agencies to gain access to advanced instruments and share knowledge. This cooperation helps build scientific capacity worldwide while accelerating discoveries about distant worlds like K218b. Education and public outreach are other important aspects. By engaging in exoplanet research, developing nations inspire their young people to pursue careers in science and technology. This creates a positive feedback loop, fostering future generations of researchers who can further advance our understanding of planets beyond our solar system. As our understanding of exoplanets grows, international collaboration will be crucial for ambitious missions to study distant worlds like K218b. Space agencies from multiple countries could pool their resources and expertise to develop advanced telescopes and spacecraft, capable of probing K218b's atmosphere and potential habitability. Funding for such missions would likely come from a combination of government space budgets, research institutions, and possibly even private sector partnerships. The high costs and long-term nature of deep space exploration necessitate sustained financial commitments over many years or even decades. The organizational structure might resemble that of the James Webb Space Telescope, with one space agency taking the lead role while others contribute specific instruments or technologies. This approach allows nations to share both the financial burden and the scientific rewards of major space endeavors. Given the potential significance of studying a super-Earth like K218b, there could also be opportunities for smaller countries or emerging space programs to participate, fostering global cooperation in the quest to understand our cosmic neighborhood.